OpenCV is one of the most important libraries in computer vision, and in this video I'm gonna walk you through 20 amazing computer vision projects so I can help you learn OpenCV. The projects range from beginner to intermediate levels, and all of them involve creating simple Python applications with a user interface for interaction. We will be working with face detection, histogram equalization, background subtraction, morphological transformations, object tracking, feature matching, image segmentation, face swapping, and much more. For each project, I will break down the code step by step, explaining every single instruction so you can fully understand how it works and how it fits in the overall project. I've spent hundreds of hours researching various tools and different resources while I was creating this video so I can give you the best quality content. All the projects were created using advanced AI tools for audio generation, resulting in a perfect native English sounding voice. So I hope you enjoy it. My name is Felipe, welcome to my channel, and now let's get started.
In this project, we will create a desktop application using Python that converts images into pencil sketches. Utilizing libraries such as OpenCV for image processing and tkinter for the graphical user interface, the application allows users to open an image file, which is then converted into a sketch through several transformations, including grayscale conversion, inversion, Gaussian blurring, and blending. The resulting sketch is displayed alongside the original image within the application window. Users have the option to save the sketch to their device in PNG format. This project combines image manipulation techniques with user-friendly GUI elements, providing an engaging way to transform everyday images into artistic sketches. We're creating a dictionary called images to store our original and sketch images, initially setting both to none. Let's define a function called openFile that will handle opening an image file for us. Here, we're using a file dialog to let the user choose an image file, and we'll store the selected file's path in FilePath. We're checking if the user actually selected a file or just closed the dialog without choosing anything. If no file was selected, we'll just exit the function and do nothing else. Now we're using OpenCV to read the selected image file and store it in the img variable. We'll call our displayImage function to show the original image, passing true to indicate it's the original. Here we're calling our convertToSketch function to transform the original image into a sketch. Now we'll display the sketch image by calling displayImage again, this time passing false to indicate it's not the original. Let's define our convertToSketch function that will transform a regular image into a sketch-like version. First, we convert the image to grayscale using OpenCV's color conversion function. Next, we invert the grayscale image to get its negative. We apply Gaussian blur to the inverted image to smooth it out. Now we invert the blurred image back. Finally, we divide the original grayscale image by the inverted blurred image to create our sketch effect. We return the resulting sketch image from our function. Let's define our displayImage function that will handle showing images in our GUI. If it's the original image, we convert it from BGR to RGB color space. Otherwise, we leave it as is. We convert our NumPy array image to a PIL image object. Now we create a tkinter compatible photo image from our PIL image. We check if we're dealing with the original image or the sketch. If it's the original, we store the PIL image in our images dictionary under the original key. If it's the sketch, we store it under the sketch key instead. We select which label to update based on whether it's the original or sketch image. We update the selected label with our new tkinter photo image. We also need to keep a reference to the image to prevent it from being garbage collected. Let's define our saveSketch function that will handle saving the sketch image. First, we check if there's actually a sketch image to save. If there's no sketch, we show an error message to the user. And then we exit the function if there's no sketch to save. We're using the file dialog to let the user choose where to save their sketch, defaulting to PNG files for easy viewing. We're checking if the user actually selected a file path. If they didn't, we'll stop here. If no file path was chosen, we're exiting the function to avoid errors. Now we're saving the sketch image to the file path the user chose, using the PNG format for high quality. We're showing a message box to let the user know their sketch was saved successfully and where to find it. Here we're creating the main window for our application using tkinter. We're setting the title of our application window to Pencil Sketch Converter, so users know what it does. We're creating a frame inside our main window to organize our widgets. We're adding our frame to the window with some padding for a nicer look. We're creating a label to display the original image. We're positioning the original image label in our frame with some padding. We're creating another label to display the sketch image. We're positioning the sketch image label next to the original image label. We're creating another frame to hold our buttons. We're adding the button frame below our image frame with some vertical padding. We're creating a button labeled OpenImage that will call the OpenFile function when clicked. We're positioning our OpenImage button in the button frame. We're creating another button labeled Save Sketch that will call the Save Sketch function when clicked. We're positioning our Save Sketch button next to the OpenImage button. Finally, we're starting our application's main event loop, which will keep our window open and responsive to user actions. In this project, we will create a simple Python application that enables users to select an image from their file system and convert it to grayscale using OpenCV. The project utilizes a graphical user interface built with tkinter, which allows users to easily navigate and interact with the application. Through a file dialog, users can browse and select an image file in various formats, such as JPG, JPEG, PNG, BMP, or TIFF. Once an image is selected, it is processed to grayscale using OpenCV's image processing capabilities, and the grayscale image is displayed in a separate window. Let's define a function called OpenFile that will handle opening an image file when the user clicks the button. Here we're using the file dialog to open a file selection window, allowing the user to choose an image file with specific extensions. We'll check if a file was actually selected by the user before proceeding. If a file was selected, we'll call our convert to grayscale function and pass the file path to it. Now let's define our convert to grayscale function that takes an image path as input. We use OpenCV's imred function to load the image from the given path. We'll check if the image was successfully loaded before proceeding. If the image wasn't loaded properly, we'll exit the function. Here's where the magic happens. We convert the color image to grayscale using OpenCV's CVT color function. We display the grayscale image in a new window titled Grayscale Image. This line waits for a key press before continuing, keeping the image window open. After a key is pressed, we close all OpenCV windows. Let's define a function to set up our user interface, taking the root tkinter window as a parameter. We set the title of our application window. Here we're setting the initial size of our window to 300 pixels wide and 150 pixels tall. We're making our window non-resizable to keep a consistent layout. This configures the first column of our grid to expand and fill available space. Similarly, this configures the first row to expand and fill available space. We create a label widget with instructions for the user, wrapping the text at 250 pixels. We position our label in the grid, adding some padding and sticking it to the top. Now we create a button that says Open Image and link it to our OpenFile function. We position our button in the grid, adding padding and making it stick to the bottom, right, and left sides. This condition checks if the script is being run directly, not imported. We create the main window of our application using tkinter. We call our setup UI function to set up the user interface. Finally, we start the tkinter event loop, which keeps our window open and responsive to user interactions. In this project, we will develop a Python application that applies a live grayscale filter to video captured from a webcam. Utilizing the OpenCV library for image processing and tkinter for the graphical user interface, the live grayscale filter program allows users to start or stop the grayscale filter with the click of a button. When active, the application captures frames from the webcam, converts them into grayscale in real time, and displays the processed video in a separate window. Users can easily switch the filter on and off using Start and Stop buttons, enhancing the interactive aspect of the project. Additionally, the application is designed to gracefully handle closure by releasing resources tied to the video capture and closing any open display windows when the user exits the program. Let's define a class called liveGrayscaleFilter, which will contain all the functionality for our liveGrayscaleFilter application. We're creating the initialization method for our class, which takes a root parameter representing the main window of our application. Here, we're storing the root window as an instance variable so we can use it throughout the class. We're setting the title of our application window to liveGrayscaleFilter. We're initializing a flag to keep track of whether the filter is running or not, starting with false. This line calls a method to set up the user interface elements of our application. We're creating a video capture object to access the default camera, usually the built-in webcam. Now we're defining a method to set up the user interface elements of our application. We're creating a start button that, when clicked, we'll call the startFilter method. This line adds the start button to our window with some vertical padding. Similarly, we're creating a stop button that will call the stopFilter method when clicked. We're adding the stop button to our window, also with some vertical padding. Here we're defining the method that will be called when the start button is clicked. We set the runFilter flag to true to indicate that the filter should start running. This line calls the process frames method to start processing video frames. Now we're defining the method that will be called when the stop button is clicked. We set the runFilter flag to false to stop the filter from running. This line closes all OpenCV windows that might be open. Here we're defining the method that processes each video frame and applies the grayscale filter. We're checking if the filter should be running. If not, we'll exit the method. If the filter isn't running, we return from the method without doing anything. We're reading a frame from the video capture object, where ret is a success flag and frame is the actual image. We're checking if the frame was successfully captured before processing it. This line converts the captured color frame to grayscale using OpenCV's CVT color function. We're displaying the grayscale frame in a window titled liveGrayscaleFilter. This line waits for a key event for 20 milliseconds, allowing OpenCV to process GoEye events. We're scheduling this method to run again after 10 milliseconds, creating a loop for continuous frame processing. This method defines what happens when the user tries to close the application window. We set the runFilter flag to false to stop the filter from running. We're checking if the video capture object is still open. If the capture object is open, we release it to free up system resources. This line closes all OpenCV windows that might still be open. Finally, we destroy the main application window, effectively closing the application. This condition checks if the script is being run directly, not imported as a module. We're creating the main window for our tkinter application. Here we're creating an instance of our liveGrayscaleFilter class, passing in the main window. This line sets up a protocol to call our onClosing method when the user tries to close the window. Finally, we call the mainLoop method on our root window, which starts the tkinter event loop and keeps our application running, allowing it to respond to user interactions and display the GUI until the user closes the window. In this project, we will develop a Python application that enables users to select and upload two images for feature matching using the ORB, Oriented Fast and Rotated Brief algorithm. Leveraging the OpenCV library, we will read the selected images in grayscale mode and detect key points and descriptors for each image. The project includes an interactive graphical user interface built with tkinter for easy image selection and displays the feature matching results using the BF-Matcher algorithm. By visualizing the top 50 matches between the two images, the application demonstrates how computer vision techniques can be applied to image processing tasks. The project aims to provide users with an intuitive experience in exploring the basic concepts of feature extraction and matching in computer vision. Let's define a function called selectImage that will allow us to choose an image file. We're declaring these variables as global so we can access and modify them from within the function. This line opens a file dialog box for the user to select an image file and stores the chosen file path in File Path. We're checking if a file was actually selected by the user. If a file was selected, we're reading it as a grayscale image using OpenCV and storing it in the img1 variable. Here we're updating the label text to show the name of the selected image file. Now we're defining another function, selectImage2, which is similar to the first one, but for selecting a second image. Again, we're declaring global variables for the second image. This opens another file dialog for selecting the second image. We're checking if a second file was selected. If a file was selected, we're reading it as a grayscale image and storing it in img2. We're updating the label for the second image with its file name. Let's define our main function, feature matching, which will perform the actual feature matching between the two images. We're checking if both images have been selected before proceeding. If either image is missing, we'll exit the function. We're creating an ORB, Oriented Fast and Rotated Brief detector object for feature detection and description. This line detects key points and computes descriptors for the first image. We're doing the same for the second image. Here we're creating a brute force matcher object with Hamming distance and cross-checking enabled. We're using the matcher to find corresponding features between the two images. This line sorts the matches based on their distance, with the best matches first. We're drawing the top 50 matches between the two images. This displays the result of feature matching in a new window. We're waiting for a key press before proceeding. After the key press, we're closing all OpenCV windows. Let's create the main window for our GUI. We're setting the title of our GUI window. We're initializing the variable for the first image, and doing the same for the second image. We're creating a button that will trigger the selectImage function when clicked. This adds the button to our GUI window. We're creating a label to show the status of the first image selection, and adding this label to our GUI window. Here we're creating a button labeled selectImage2 that, when clicked, will trigger the selectImage2 function to choose the second image for our feature matching process. We're using the pack method to add our selectImage2 button to the main window, which will display it in the GUI. Now we're creating a label that will show the status of image 2, initially set to not selected, which will be updated once an image is chosen. We're adding the image 2 status label to our main window using the pack method, so it appears in the GUI below the selectImage2 button. Here we're creating another button labeled Match Features that, when clicked, will call the feature matching function to compare the two selected images. We're using pack again to add the Match Features button to our main window, placing it below the previously added elements in the GUI. Finally, we're calling mainLoop on our root window, which starts the GUI event loop and keeps our application running, waiting for user interactions. In this project, we will create an interactive image segmentation tool using Python's tkinter and OpenCV libraries, which enables users to easily segment images through a graphical user interface. The application provides a simple and intuitive interface for selecting an image file, upon which it carries out image segmentation using watershed algorithm, a technique commonly used for distinguishing different objects within an image. The tool converts the selected image to grayscale, applies thresholding and morphological operations to enhance features, and finally uses distance transform for precise foreground extraction. The result is a segmented image with boundaries outlined, displayed to the user in a separate window, demonstrating how computer vision can be efficiently applied for object separation in digital imagery. Let's define a function called selectImage that will handle the image selection process. We'll use the file dialog to open a file chooser window and store the selected file path in the file path variable. Now we'll check if a file was actually selected by the user. If no file was selected, we'll exit the function early. We'll use OpenCV to read the selected image file and store it in the image variable. Let's convert the image from BGR color space to RGB color space, which is more commonly used. Now we'll call our segmentImage function, passing in the loaded image to perform the segmentation. Here, we're defining the segmentImage function that will handle the actual image segmentation process. First, we'll convert the input image to grayscale, which is often the first step in image processing. Now we'll apply Otsu's thresholding to create a binary image, which helps separate objects from the background. We'll create a 3 kernel of ones, which we'll use for morphological operations. Let's apply the morphological opening operation to remove small noise in the image. We'll dilate the image to get a sure background area. Now we'll apply the distance transform to get the distance of each pixel to the nearest 0 pixel. We'll threshold the distance transform to get the sure foreground area. Let's convert the sure foreground to 8-bit unsigned integer type. We'll subtract the sure foreground from the sure background to get the unknown region. Now we'll use connected components to label the sure foreground areas. We'll add 1 to all labels so that sure background is not 0, but 1. Let's mark the unknown region with 0. Now we'll apply the watershed algorithm to segment the image. We'll mark the boundaries of the segments in red on the original image. Finally, we'll call the display segmented image function to show the result. Here, we're defining the display segmented image function to show the segmented image. We'll use OpenCV to display the segmented image, converting it back to BGR color space for proper display. This line waits for a key press before closing the image window. After the key press, we'll close all OpenCV windows. Let's create the main window for our GUI application using tkinter. We'll set the title of our application window. Now we'll create a label with instructions for the user. We'll add the label to our window with some padding. Let's create a button that will trigger the image selection process when clicked. We'll add the button to our window with some padding. Now we'll set the initial size of our application window. Finally, we'll start the main event loop of our GUI application. In this project, we will develop a simple graphical user interface (GUI) application using Python that allows users to easily select multiple images and automatically stitch them together into a panorama. By leveraging the OpenCV library and its powerful image processing capabilities, our program will guide users to select at least 2 images through a file dialog box. Upon selection, the images are read, processed, and seamlessly stitched using OpenCV's stitching functionality. The result is then displayed within the application window using the tkinter library. We define a function called openFiles that will handle the process of selecting image files. We use the tkinter file dialog to open a file selection window, allowing the user to choose multiple image files. We check if the user selected fewer than 2 files, as we need at least 2 images for stitching. If fewer than 2 files were selected, we show an error message to the user. We exit the function early if not enough files were selected. We start a loop to iterate through each selected file. We add each selected file path to our image paths list. We display a success message showing how many images were selected. We define a function called stitchImages that will handle the image stitching process. We create a local variable paths and assign it the value of our global image paths list. We check again if we have at least 2 images to stitch. If we don't have enough images, we show an error message. We exit the function early if there aren't enough images. We create an empty list called images to store the loaded image data. We start a loop to iterate through each image path. We use OpenCV to read and load each image from its file path. We check if the image was successfully loaded. If an image couldn't be loaded, we show an error message. We exit the function early if an image couldn't be loaded. We add the successfully loaded image to our images list. We create an instance of OpenCV's Stitcher class, which will perform the image stitching. We call the stitch method on our Stitcher object, passing in our list of images, and get back a status code and the stitched panorama. We check if the stitching was successful by comparing the status to OpenCV's success constant. If stitching failed, we show an error message. We exit the function early if stitching failed. If stitching was successful, we call our displayImage function to show the result. We show a success message to indicate that stitching was completed. We define a function called displayImage that will handle showing the stitched image in our GUI. We convert the OpenCV image from BGR color space to RGB for proper display. We create a partial image object from our RGB numpy array. We create a tkinter-compatible photo image from our PIL image. We update our image panel in the GUI with the new image. We keep a reference to the image to prevent it from being garbage collected. We create the main window for our tkinter GUI application. We set the title of our main window. We create an empty list called image paths to store the file paths of the selected images. Now we're creating a button labeled Open Images and assigning it to the variable Open button. When clicked, it will call the OpenFiles function to let us select images. Here, we're making another button called Stitch Button with the label Stitch Images, which will trigger the Stitch Images function when pressed to combine our selected images.
We're setting up a label widget called Panel, which we'll use later to display images or messages in our GUI.
This line adds our Open Images button to the GUI window, giving it some vertical padding of 10 pixels for a nicer look. Similarly, we're adding the Stitch Images button to our GUI, also with 10 pixels of vertical padding. Here we're placing our Panel widget in the GUI window, giving it both horizontal and vertical padding of 10 pixels for better spacing. Finally, we start the main event loop of our tkinter application, which keeps our GUI running and responsive to user interactions. In this project, we will develop a graphical user interface using Python to perform morphological transformations on images. By using libraries such as OpenCV and tkinter, we set up an application where users can load an image and apply various transformations like erosion, dilation, opening, closing, gradient, top hat, and black hat using dynamic control options. The user can select different morphological operations from a drop-down menu and adjust the kernel size using a slider to see real-time effects on the image. This project blends image processing capabilities with an interactive GUI, providing an educational and practical tool for understanding morphological image transformations. We're creating the main window for our application using tkinter. Let's set the title of our application window to Morphological Transformations. Now we're defining a function called loadImage that will help us open an image file. We're declaring these variables as global so we can use them throughout our script. This line opens a file dialog for the user to select an image file. Here we're reading the selected image file in color mode using OpenCV. We're checking if an image was successfully loaded before proceeding. If an image is loaded, we're calling the Apply Transformations function to process it. We're defining the Apply Transformations function that will handle our image processing. Again, we're declaring these variables as global for use within this function. If no image is loaded, we'll exit the function without doing anything.
We're getting the kernel size from a scale widget, which we'll define later.
Here we're getting the selected operation from a variable, which we'll set up later. We're creating a kernel, a small matrix for our morphological operations. These conditional statements apply different morphological transformations based on the selected operation. We're storing the transformed image in the imgDisplay variable. This line displays our transformed image in a new window. We're waiting for a key press before closing the image window. Finally, we're closing all OpenCV windows when we're done. We're creating a list called Options that contains the names of different morphological operations we can apply to our image. Here, we're creating a tkinter string var object named var associated with our root window, which will store the currently selected operation from our drop-down menu.
Now we're creating a drop-down menu widget called Operation Menu, using tkinter's option menu, which will display our morphological operations and allow the user to select one. We're adding our drop-down menu to the main window using the pack method, which will display it in the GUI.
Here we're creating a horizontal slider widget called Kernel Scale that allows the user to select a kernel size between 1 and 20 for our morphological operations. We're setting the default value of our kernel size slider to 5. We're adding our kernel size slider to the main window, so it appears in the GUI below the drop-down menu.
Now we're creating a button labeled Load Image that, when clicked, will call the Load Image function to allow the user to select an image file.
We're adding our Load Image button to the main window, displaying it below the kernel size slider.
Here we're binding the left mouse button release event on our kernel size slider to call the apply transformations function. So the image updates when the user changes the kernel size.
We're setting up a trace on our string var to call the apply transformations function whenever the selected operation in the drop-down menu changes. This line starts the main event loop of our tkinter application, which keeps the GUI running and responsive to user interactions. Finally, we're calling this OpenCV function to close any remaining image windows when the application is closed. In this project, we will develop a Python application for detecting lines in images using the Hough transform technique. Utilizing OpenCV and tkinter libraries, the application presents a user-friendly interface where users can select an image file for processing. After loading an image, users can adjust the canny edge detection and Hough transform thresholds via interactive sliders, providing flexibility in line detection sensitivity. The application then processes the image to detect lines and displays the result in a new window, highlighting the identified lines in red. We're defining a class called line detection app, which will contain all the functionality for our line detection application. This is the constructor method for our line detection app class, which initializes the application with a root window passed as an argument. We're saving the root window as an instance variable so we can use it throughout the class. Here we're setting the title of our application window to Hough transform line detection. We're creating a label widget with instructions for the user to select an image. This line adds the label we just created to our application window. We're creating a button that, when clicked, will call the select image method to let the user choose an image file. This adds the choose image button to our application window. We're creating a horizontal slider that allows the user to adjust the canny edge detection threshold from 50 to 150. This sets the initial value of our canny threshold slider to 100. We're adding the canny threshold slider to our application window. Here we're creating another horizontal slider for adjusting the Hough transform threshold, ranging from 50 to 200. This sets the initial value of our Hough threshold slider to 100. We're adding the Hough threshold slider to our application window. We're creating a detect lines button that will call the detect lines method when clicked.
This adds the detect lines button to our application window.
We're initializing the image path variable to none, which will later store the path of the selected image. This method will be called when the user clicks the Choose Image button to select an image file.
We're opening a file dialog for the user to select an image, restricting the file types to common image formats.
This updates the label text to show the path of the selected image. This method will be called when the user clicks the Detect Lines button to process the selected image. We're checking if an image has been selected before proceeding with line detection.
If no image is selected, we update the label to inform the user.
We exit the method early if no image is selected. We're reading the selected image using OpenCV's imread function. This converts the image to grayscale, which is necessary for edge detection. We're applying canny edge detection to the grayscale image using the threshold value from our canny slider. This applies the Hough transform to detect lines in the edge image using the threshold from our Hough slider. We're checking if any lines were detected before attempting to draw them. We're iterating through each detected line, represented by its RO and theta values. We're calculating the cosine of the line's angle.
Here we're calculating the sine of the line's angle.
We're calculating the x-coordinate of a point on the line. This calculates the y-coordinate of a point on the line. We're calculating the x-coordinate of one endpoint of the line segment. This calculates the y-coordinate of one endpoint of the line segment. We're calculating the x-coordinate of the endpoint for our line by subtracting 1,000 times the negative of b from x over so, and then converting it to an integer. Similarly, we're calculating the y-coordinate of the endpoint for our line by subtracting 1,000 times a from y0 and converting the result to an integer.
Now we're using OpenCV to draw a red line on our image, starting from point x1, y1, and ending at x2, y2, with a thickness of 2 pixels.
This line displays our image with the detected lines in a window titled Detected Lines. Here we're telling the program to wait indefinitely until a key is pressed, keeping our image window open. After a key is pressed, this line closes all OpenCV windows, cleaning up our display. This conditional statement checks if our script is being run directly not imported, which is typically used to separate code that should only run when the script is the main program. We're creating the root window for our tkinter application, which will serve as the main container for our GUI elements. Here we're creating an instance of our line detection app class, passing in the root window we just created. Finally, we start the tkinter event loop, which keeps our GUI running and responsive to user interactions. In this project, we will explore the implementation of multiple object tracking algorithms using OpenCV and Python. The goal is to allow users to select from a variety of predefined trackers to track an object within a video feed. Users can choose a tracker type through a simple interface and can either input the path to a video file or use a webcam for real-time tracking. The program initializes the selected tracker, lets the user specify a region of interest on the first frame of the video, and continuously updates and displays the tracking results. If the tracker loses the object, a failure message is displayed, all while providing the option to exit the application by pressing the escape key. We're defining a function called selectTracker that takes a tracker type parameter, which will help us choose the right tracking algorithm. We're starting an if-else chain to check which tracker type was requested, beginning with the boosting tracker. If boosting was selected, we're returning a new instance of the boosting tracker from OpenCV's legacy module. We're checking if the MIL tracker was requested. If MIL was selected, we're creating and returning a new MIL tracker instance. Now we're checking if the KCF tracker was requested. For the KCF tracker, we're creating and returning a new KCF tracker instance. We're checking if the TLD tracker was requested. If TLD was selected, we're creating a TLD tracker from the legacy module and returning it. Now we're checking if the median flow tracker was requested. For median flow, we're creating and returning a median flow tracker from the legacy module. We're checking if the MOSI tracker was requested. If MOSI was selected, we're creating and returning a MOSA tracker from the legacy module. Now we're checking if the CSRT tracker was requested. For the CSRT tracker, we're creating and returning a new CSRT tracker instance. If none of the known tracker types match, we'll handle it as an error. We're raising a value error with a message indicating that the tracker type is not supported. We're defining the main function that will run our object tracking program. We're creating a list of all the supported tracker types that the user can choose from. We're printing a message to prompt the user to select a tracker type. We're starting a loop to iterate through the tracker types, giving each one a number starting from 1. We're asking the user to input a number for their chosen tracker and converting it to an index, subtracting 1 because lists are 0 indexed. We're using the user's choice to select the corresponding tracker type from our list. We're calling our selectTracker function with the chosen tracker type to create the appropriate tracker object. We're asking the user to input a path to a video file or leave it blank to use the webcam. We're checking if the user didn't provide a video path. If no video path was given, we're setting up video capture from the default webcam, device 0. If a video path was provided, we'll use that instead. We're setting up video capture using the provided video file path. We're checking if the video, file or webcam was successfully opened. If the video couldn't be opened, we're printing an error message. After printing the error message, we're exiting the program. We're reading the first frame from the video and storing it, along with a Boolean indicating if the read was successful. We're checking if the frame was successfully read. If we couldn't read the frame, we're printing an error message. After printing the error message, we're exiting the program. We're using OpenCV's selectROI function to let the user draw a bounding box around the object they want to track. We're initializing the tracker with the first frame and the bounding box the user selected. We're starting an infinite loop that will keep running until we explicitly break out of it. Here we're reading a frame from our video source, and OK will tell us if the read was successful. We're checking if the frame wasn't read successfully, which could happen if we've reached the end of the video. If we couldn't read a frame, we're exiting the loop since there's no more video to process. We're updating our tracker with the new frame and getting back a Boolean OK and a bounding box bbox if tracking was successful. We're checking if the tracker successfully found our object in this frame. If tracking was successful, we're defining the top left point of our bounding box. Now we're defining the bottom right point of our bounding box. We're drawing a blue rectangle on our frame using the points we just calculated to show where the tracked object is. If tracking wasn't successful, we'll do something else instead of drawing a rectangle. When tracking fails, we're adding text to the frame to indicate that tracking has failed. We're adding text to show what type of tracker we're using. We're adding instructions for the user on how to quit the program. Now we're displaying our frame with all the added information in a window titled Tracking. If ESC was pressed, we're breaking out of our main loop to end the program. After we finish processing all frames, we're releasing our video capture object to free up resources. Finally, we're closing all the OpenCV windows we've created. This is a common Python idiom that checks if this script is being run directly, not imported. If the script is being run directly, we're calling our main function to start the program. In this project, we will develop a motion detection application using Python, OpenCV, and tkinter. The application provides a user-friendly interface to start and stop motion detection through a simple GUI with buttons for controlling the detection process. When motion detection is activated, the application captures video feed from a webcam, processes the frames to detect motion based on differences between successive frames, and highlights moving objects with green rectangles. This project demonstrates the integration of computer vision techniques with a graphical user interface to create an interactive tool for real-time motion detection. We're defining a new class called Motion Detection App, which will contain all the functionality for our motion detection application. This is the constructor method for our motion detection app class, which takes a root parameter representing the main window of our application. We're storing the root window as an instance variable so we can access it throughout the class. Here we're setting the title of our application window to motion detection. We're setting the initial size of our application window to 300 pixels wide by 150 pixels tall. We're creating a start detection button using ttk.button, which will call the start detection method when clicked. We're adding the start button to our window with some vertical padding. We're creating a stop detection button, initially disabled, which will call the stop detection method when clicked. We're adding the stop button to our window with some vertical padding. We're creating a label to display the current status of our motion detection. We're adding the status label to our window with some vertical padding. We're initializing a flag to keep track of whether motion detection is currently running. We're initializing a variable to store our video capture object, which we'll use later for accessing the camera. We're defining a method called start detection, which will be called when the start button is clicked. We're setting the running flag to true to indicate that motion detection is now active. We're disabling the start button since detection is now running. We're enabling the stop button so the user can stop the detection. We're updating the status label to show that motion detection is now running. We're calling the detect motion method to start the actual motion detection process. We're defining a method called stop detection, which will be called when the stop button is clicked. We're setting the running flag to false to indicate that motion detection should stop. We're re-enabling the start button so the user can start detection again. We're disabling the stop button since detection is no longer running. We're updating the status label to show that motion detection is no longer running. We're checking if we have an active video capture object. If we have an active video capture, we're releasing it to free up the camera. We're closing all OpenCV windows that might have been opened during motion detection. We're defining the detect motion method, which contains the main logic for motion detection. We're initializing our video capture object to access the default camera, index 0. We're reading the first frame from the camera, ignoring the return value, hence the underscore. We're converting the previous frame to grayscale for easier processing. We're applying Gaussian blur to the grayscale image to reduce noise. We're starting a loop that will continue as long as motion detection is running. We're reading a new frame from the camera in each iteration of the loop. We're converting the new frame to grayscale. We're applying Gaussian blur to the new grayscale frame to reduce noise. We calculate the difference between the previous frame and the current frame to detect any changes, which helps us identify motion. Now we apply a threshold to the difference frame, turning pixels above a certain intensity, 25 to white, 255, and below to black, 0, creating a binary image. We dilate the thresholded image to fill in small holes and make the white areas larger, which helps in detecting larger motion areas.
Here we find the contours, outlines of the white areas in the threshold image, which represent areas of motion.
We start a loop to process each contour we found in the previous step.
We check if the area of the contour is smaller than 500 pixels, and if so, we skip it to ignore small movements.
If the contour area is less than 500, we continue to the next contour without processing this one. For contours larger than 500 pixels, we calculate the bounding rectangle coordinates and dimensions. We draw a green rectangle around the area of detected motion on the original frame. We display the frame with the green rectangles in a window titled Motion Detection. We wait for 1 millisecond for a key press and store the ASCII value of the pressed key. We check if the user pressed AQ to quit or if the running flag is false. If the condition is true, we break out of the loop and stop the motion detection. We update the previous frame with the current frame for the next iteration. After breaking out of the loop, we call the stop detection method to clean up resources. We check if this script is being run directly, not imported as a module. We create the main window for our tkinter application.
We create an instance of our motion detection app class, passing the main window as an argument.
Finally, we start the tkinter event loop, which keeps our application running and responsive to user interactions.
In this project, we will develop a user-friendly document aligner application using Python, which conveniently allows users to load, process, and view images of documents. Leveraging OpenCV and tkinter libraries, this application can automatically detect and correct the orientation of scanned or photographed documents. The program converts loaded images to grayscale, applies thresholding to isolate the document content, and calculates the optimal rotation angle required to properly align the document. Through a simple graphical interface, users will be able to load images and see the corrected document displayed on their screen, ensuring that any skewed or misaligned documents are automatically adjusted for easy reading or further processing.
We're defining a function called rotateDocument, which takes an image as an argument and aims to automatically straighten it by detecting its content's angle and rotating accordingly. First, we convert the image to grayscale using OpenCV to simplify further processing since color information isn't needed for detecting orientation. We apply a binary threshold to the grayscale image, turning pixels with a value above 240 to white and everything else to black, creating a high contrast image. We invert the binary image so that the content is white and the background is black, which helps in finding the document's edges easily. Here we identify all the white pixels coordinates in the inverted image that represent the document's content. We then check if there are any content pixels found in the image, and if not, skip the rotating since there's nothing to adjust. If no content is detected, we simply return the original image as it is. We obtain a minimum area rectangle that tightly encloses all the detected content, giving us the document's boundaries. From this rectangle, we extract the angle of rotation needed to straighten the document. The code assumes only minor angle corrections are needed to align the bounding box properly, accounting for how CV2 min area rect defines angles. If the angle is less than 45 degrees, it indicates a clockwise adjustment, so the correction is negative angle. Otherwise, for angles closer to vertical, the correction is counterclockwise, calculated as 90 minus angle. We then retrieve the dimensions of the original image to help position the rotation effectively. The center of the image is calculated to use as the rotation center, ensuring the document stays centered after rotation. Next, we compute the rotation matrix using the determined center and angle, which helps in transforming the image. With the rotation matrix, we rotate the image using warp affine, ensuring smooth borders around the transformed image. Finally, we return the rotated image, which should now be aligned based on the detected document content. We're defining another function called loadImage, which will help us load an image from the system files for further processing. Within this function, we open a file dialog to allow the user to select an image from their computer to process. We start by checking if the file path provided is empty or none. If file path is empty, we exit the function because there's nothing to process. Here we load the image from the specified file path into a variable image using OpenCV's imread function. We pass our loaded image to rotate document, which processes and aligns the document, capturing the result in aligned image.
Next, we check if rotate document successfully aligned the image, meaning aligned image is not none.
If alignment was successful, we display the aligned image using our custom display image function. Otherwise, if alignment failed and aligned image is none, we show an error message to alert the user that document content could not be detected. In display image, we convert the image from BGR to RGB format using OpenCV's CVT color so it displays correctly in tkinter. We then convert the OpenCV image to a PIL image using image from array.
After conversion, we turn the PIL image into an image TK photo image, which tkinter can use.
We draw the image onto our tkinter canvas, starting at the top left corner. Here we create the main tkinter application window and assign it to App. We set the title of our application window to Document Aligner. We specify the size of the application window to be 800 pixels wide and 900 pixels high. We create a drawing area, canvas, within the application window, making it 800 by 800 pixels.
We use Pack to add the canvas to our application, allowing it to expand and fill the available space.
We set up a container widget, button frame, to hold our button at the bottom of the app. We position button frame at the bottom, stretching it horizontally across the app. We create a button labeled Load Image that runs Load Image when clicked, placing it inside button frame. We position the button to the left inside the button frame with a little space around it. Finally, we start the tkinter event loop with app.mainLoop, keeping our app responsive to user actions. In this project, we will develop a Python-based live video augmentation application using the OpenCV and tkinter libraries. The application captures live video feed from the webcam and provides users with real-time video augmentation options. Users can select from various video effects such as grayscale, sepia, and sketch, allowing them to see their live feed with these effects applied. Additionally, the application includes a brightness slider for adjusting the video feed's brightness level. The interface is built using tkinter, with a simple and user-friendly design featuring a combo box for effect selection and a quit button to exit the application. Let's define our main application class called Video Augmentation App, which will handle all the functionality of our video augmentation tool. We're creating the initialization method for our class, which takes a window parameter to set up the main application window.
Here we're storing the past window object as an instance variable, so we can use it throughout the class.
We're setting the title of our application window to Live Video Augmentation. This line initializes the video capture from the default camera, usually the built-in webcam, using OpenCV. We're creating a tkinter string var to store the currently selected augmentation type, initially set to none. This calls a method we'll define later to create and set up all the UI widgets for our application.
Here, we're calling an update method that we'll define later to continuously refresh the video feed and apply augmentations.
Now we're defining the method to create all the UI elements for our application. This creates a label widget where we'll display the video feed. We're positioning the video label in the grid layout, spanning across 4 columns. This creates and positions a label for our augmentation drop-down menu. Here we're creating a drop-down menu, combo box, for selecting different augmentation types. We're positioning the augmentation selection drop-down in the grid layout. This creates a horizontal slider for adjusting the brightness of the video. We're setting the initial value of the brightness slider to 50, middle position. Here we're positioning the brightness slider in the grid layout. This creates a quit button that will call the quit app method when clicked. We're positioning the quit button in the grid layout.
Now we're defining the update method that will continuously refresh the video feed and apply augmentations.
This line captures a single frame from the video feed. We're checking if the frame was successfully captured before proceeding. Here, we're applying the selected augmentation to the captured frame. This line adjusts the brightness of the frame based on the slider value. We're calling a method to display the processed frame in the UI. This schedules the update method to be called again after 10 milliseconds, creating a loop. Now we're defining a method to apply different augmentations to the video frame. We're getting the currently selected augmentation type from the drop-down menu. This checks if the grayscale augmentation is selected. If grayscale is selected, we convert the frame to grayscale using OpenCV. We then convert the grayscale frame back to BGR format for consistency. This checks if the sepia augmentation is selected. This line ensures that all pixel values stay within the valid range of 0 to 255 after the sepia transformation.
Now we're checking if the augmentation type is set to Sketch, which will apply a sketching effect to our video frame.
First, we convert our color frame to grayscale using OpenCV's CVT color function, which is necessary for creating the sketch effect.
Next, we invert the grayscale image using the bitwise not function, essentially creating a negative of our original image.
We then apply a Gaussian blur to the inverted image, using a 21:21 kernel size, which helps to smooth out the image and reduce noise. After blurring, we invert the image again, bringing it back to a positive form, but with the blur effect applied. Now we divide the original grayscale image by the inverted blurred image, which creates the sketch-like effect we're looking for. Finally, we convert the sketched frame back to a BGR color space so it's compatible with our display function. We return the processed frame, which now has the sketch effect applied. Here, we're defining a method to adjust the brightness of our video frame. We get the current value of the brightness slider from our GUI. Using OpenCV's convertScaleAbs function, we adjust the frame's brightness based on the slider value, dividing by 50 to get a suitable range. We return the brightness-adjusted frame. This method is responsible for displaying the processed frame in our GUI. First, we resize the frame to a standard size of 600 by 480 pixels for consistent display. We encode the image as a PNG and convert it to bytes, which is necessary for creating a tkinter-compatible image. We create a tkinter photo image object from our encoded image data. We update the image attribute of our video label with the new frame. We configure the video label to display the new image. This method is called when we want to close our application. We release the video capture object to free up system resources. Finally, we destroy the tkinter window, effectively closing our application. This conditional checks if the script is being run directly, not imported as a module. We create the main tkinter window for our application. We instantiate our video augmentation app class, passing in the tkinter root window. Lastly, we start the tkinter event loop, which keeps our application running and responsive to user input. In this project, we will develop a barcode scanning application using Python, integrating several libraries such as OpenCV, PySbar, and tkinter. The project involves capturing video frames through a webcam to detect and decode barcodes in real time, providing functionality to save the scanned data into a log file for future reference. Additionally, users can select image files for barcode scanning, with options to save the results, and view the logs of previously scanned barcodes. Featuring a graphical user interface, the application prompts users with options to start scanning from a webcam, select an image file for barcode detection, and review saved logs, offering a comprehensive barcode scanning solution. We're defining a function called scanBarcode that takes a video frame, a Boolean to decide if we want to log results, and a log file name as its parameters. In this line, we're converting the colored frame into a grayscale image for easier barcode detection. Here we use the decode function from the PySbar package to detect and decode any barcodes in the grayscale image. We're initializing an empty list to store the details of any barcodes that we successfully scan. This line starts a loop to iterate through each barcode found in the image. Inside the loop, we're decoding the barcode data from binary to a UTF-8 string. We're retrieving the type of barcode, like QR code or code 128, from the detected barcode object.
We're converting the polygon points of the barcode bounding box into a NumPy array with integer type.
Here we're reshaping the points array to prepare it for drawing a polygon on the frame. We draw the detected barcode's boundary on the frame as a green polygon line using OpenCV's polylines method. We're getting the rectangle that encloses the barcode, which provides coordinates for placing text. Using CV2@put_text, we display the barcode data and type as text on the frame near the barcode position, enhancing the user interface.
We add the decoded barcode data and its type to the scanned data list to keep a record of what was scanned.
This line checks if logging is enabled, meaning whether or not we should write the scanned data to a file. If logging is enabled, we call save to file to write the barcode info to the specified log file. Finally, we return the modified frame and the list of scanned data for further processing or display. We define a helper function called save to file to handle writing barcode data and type to a specified log file. This opens the log file in append mode so that we can add new entries without overwriting existing data. We're creating a timestamp string to log when each barcode was scanned, formatted for easy reading. Here we define another function, startScanner, that handles capturing video from a camera to continuously scan for barcodes. We initialize video capture with OpenCV, setting it to use the camera at index 2 to get frames from the specified camera. We specify the default file name for logging scanned barcode results.
We start an indefinite loop to continuously capture frames and process them until a break condition is met.
Here we're reading a frame from the camera, where ret indicates success and frame contains the captured image. We check if the frame capture was unsuccessful, which would mean something went wrong. If the frame wasn't successfully captured, we exit the loop to stop processing frames. We call scan barcode on the current frame, intending to log results, and capture the returned processed frame and scanned data.
We display the processed frame with detected barcodes and their data in a window labeled Barcode Scanner.
We check if the user presses the Q key, which would signal that they want to quit the scanning session. If EQ is pressed, we break out of the loop to stop capturing frames and close the scanner. Once we've stopped capturing frames, we release the video capture object to free the camera. This function call closes all OpenCV windows that were opened during the scanning session. Finally, we show a message box to inform the user that the scanner has been closed and the results have been saved. Here we're defining a function called selectFile, which will be responsible for opening a file dialog to select an image containing a barcode. This line checks if the user has selected a file. If so, the block of code beneath it will run. We're reading the selected image file into memory using OpenCV's imread function, which will allow us to process it.
We display the processed image in a window titled Barcode Scanner to show the user the scanned results.
This checks whether scanning the image produced any barcode data, and if so, it executes the following block of code. If the user chooses yes to save the results, we proceed with the next steps. We call the function saveResults_to_file to write the scanned barcode data to a text file, passing in the data and the original file path for context.
We wait for any key press in the OpenCV window to allow the user to view the image before closing it. 0 means it waits indefinitely.
Finally, we close all OpenCV windows to clean up after displaying the image. Here, we're defining a new function called saveResults_to_file, which stores the scanned barcode information into a file tied specifically to the source image file name.
We're opening a new text file with the name log file for writing, ensuring we have a valid file handle F to use within the block.
We iterate over each piece of data we have scanned, including the actual barcode information and its type. We're defining a function named viewLogFile, which will display the contents of a file storing scan logs to the user if it exists. We specify the default file name for logging scanned barcode results. This checks if the specified log file does not exist, which helps us decide whether to proceed with viewing or alert the user. We promptly exit the function early if no log file is found to prevent trying to read a non-existent file. If the log file exists, we open it for reading, assigning f as our file handle so we can process the contents. We read all lines from the file into a variable called logs, capturing the full content into a list of strings. We create a new top-level window using tkinter to display the log content independently of the main app window. We create a text widget on the log window to display the log content, specifying word wrapping, and setting an initial size. We insert the logs into our text widget, starting at the very first line, joining them into one block of text. We disable the text widget to prevent any editing of the log content, ensuring it's view only. We pack the text widget into the window using some padding to make the interface cleaner. We are initializing our main application window using tkinter, which will serve as the base of our GUI. We pack this start button into the app with a little vertical padding to make it look good. We add this button into our application, ensuring consistent spacing and layout using padding. We pack this final button into the application with padding to maintain consistent styling and layout. We're creating a label widget in our tkinter application to inform users that they can press Q to exit, setting the text color to blue for visibility. Now, we're adding some spacing by packing the label into the application window with a vertical padding of 5 pixels to make it look neat. Finally, we start the main event loop of the tkinter application, which will keep the window open and responsive until we close it. In this project, we will develop a Python application using OpenCV and tkinter for performing background subtraction on video files. The application features a user-friendly interface, allowing users to select a video file using a file dialog, toggle between displaying the original frames and the foreground mask, and optionally save the processed video with the foreground mask applied. The application employs OpenCV's moag2 background subtractor to isolate moving objects from the background. Furthermore, it includes a progress bar to provide real-time feedback on the processing status and ensures the processed video can be saved seamlessly if the user selects this option. The program ends gracefully, releasing all resources and closing all windows when finished or upon user command. Here, we're defining a new class named Background Subtraction App, which will contain all the functionalities and UI components of our application. We start by defining the constructor method init for our class, which initializes the application with a root window provided by tkinter. We assign the root window passed to the constructor to an instance variable self.root, so it can be accessed throughout the class. We set the title of the window to Background Subtraction App, which will appear at the top of the application window. We create a tkinter label widget to prompt the user to select a video file, displaying video path on the window. We place the video label on the grid at row 0, column 0, with a small padding around it using pad X and pad E to make the interface look nicer. Here we create an entry widget where users can type in or see the path of the selected video file, setting its width to 50 characters. We position the entry widget right next to the video label in the grid layout at row 0, column 1, with some padding for space. We add a Browse button to the GUI, which when clicked, calls the Browse Video function to help the user select a video file. The button is placed in the third column of the first row with a bit of padding to make it aesthetically pleasing.
Next, we add another label widget to serve as a heading for display options that can be toggled by the user, labeled Display Options.
We place the Display Options label on the grid at row 1, column 0, with padding for spacing. We define a Boolean variable to keep track of whether the original video frame is displayed, initializing it to true. A check button widget is added to let users toggle the display of the original video frame on or off, tied to the Show Original var. We position this checkbox in the grid at row 1, column 1, with padding for neat placement. Similarly, we create another Boolean variable for controlling the display of the foreground mask, also initialized to true. Another check button widget is created that allows users to toggle the display of the foreground mask. Synchronized with Show Mask var, this checkbox is placed in row 1, column 2 in our layout, aligned with the original frame checkbox. We prepare a Boolean variable to let users decide if they want to save the processed video, defaulting to false. We add a checkbox for whether to save the processed video, linked to Save Video var, so the user can toggle this option. This Save Video checkbox is positioned at row 2, column 1 of the grid, fitting below the previous options. A Start button is added, which users will click to begin processing the video, calling Start Processing method on click. We center the Start button in the grid at row 3, making it span 2 columns, with padding to enhance the layout. We create a Quit button that, when pressed, will close the application by invoking root quit. The Quit button is positioned below the Start button, at row 4 spanning 2 columns, also with padding for spacing.
We add a progress bar to the application using tkinter's TTTK module to visualize the processing progress in a horizontal orientation of 400 units long.
This progress bar is placed at row 5, covering all 3 columns, with extra padding at the top and bottom for clarity and styling.
We're using a file dialog to let the user select a video file from their system, filtering the choices to MP4 files, or showing all files as an option.
If the user has selected a file, the next steps will execute. We clear the current entry in the video entry field to prepare it for new input. We populate the entry field with the path of the newly selected video file. We define a method called Start Processing that will handle initiating the video processing steps. We retrieve the path of the video file from the entry field to use it in the processing steps. We check if no video path has been provided, in which case we stop further processing. If there's no video path, we exit the function early without doing anything else. We verify if the given video path is pointing to an actual file on the disk. If the file path is invalid, we print a message to inform the user. We exit the function if the file path was invalid, stopping any further processing. We create a video capture object to open the video file, preparing to read frames from it. We set up a background subtractor, which will help us separate moving objects from the static background in the video. We determine the total number of frames in the video, which we'll use to track and display progress. We configure a progress bar to the total number of frames, setting its maximum value for updating progress later. We check the user setting to see if they want to save the processed video to disk. We initialize a variable to potentially hold a video writer object if saving the video is desired. If the user has opted to save the processed video, we prepare to set up the video writer. We retrieve the width of the video frames to use it for video writing configuration. We also retrieve the height of the frames, necessary for saving the video correctly. We find out the frames per second, FPS, of the video to ensure that we write the video at the correct speed. We create a video writer object to save the processed video as out.mp4, setting it for monochrome output. We initialize a frame index to 0, which will help us keep track of which frame we're currently processing. We enter an infinite loop that will continue until we reach the end of the video frames. We attempt to read the next frame from the video, storing whether it was successful and the frame data itself. If reading a frame fails, it likely means we've reached the end of the video. We exit the loop once no more frames are left to read. We apply the background subtractor to the current frame to get the foreground mask, isolating moving objects. If the user opted to save the video and we have a writer set up, we proceed to the saving step. We write the current foreground mask frame to the output video file, recording our processed video. Here we're displaying the current frame being processed in a window titled Original Frame, using OpenCV's mShow function. We're checking if the Show Mask option is enabled by the user in the GUI. If the Show Mask option is active, we display the foreground mask in a separate window titled Foreground Mask. We're incrementing the frame index by 1 to track the progress through the video. This command ensures that the GUI is updated in real time to reflect any changes made during the loop, like the progress bar updates. We wait for 30 milliseconds to capture any key press, and if the Q key is pressed, we exit the loop and end the video processing. When the Q key is detected, we break out of the loop to stop further processing. We release the video capture object to free up resources after all frames have been processed. We check if there is an output video file object to ensure it was created and is valid. We release the video writer object to save and close the output video file safely. This command closes all the OpenCV windows that were created during the process to clean up the display. If the user has opted to save the processed video, we prepare to set up the video writer. If video saving was enabled, we inform the user that the video has been successfully saved as out.mp4. This line checks if the script is being run directly or being imported as a module, only executing the following block if it's run directly. We create the main tkinter application window, which will host our application's GUI. We initialize our application by creating an instance of the background subtraction app class, passing the tkinter root window to it. We start the kinter event loop, which makes the GUI responsive and able to handle user interactions. In this project, we will develop a Python application that aids in detecting and counting coins from images using OpenCV and a user-friendly graphical interface with tkinter. The application begins by allowing users to select an image file through a file dialog box. Users can then fine-tune the image processing parameters, such as blur kernel size, threshold value, and erosion iterations, using on-screen sliders to enhance detection accuracy. The process involves converting the image to grayscale, applying Gaussian blur, and thresholding to highlight coins, and using erosion techniques to isolate individual coins. After processing, the detected coins are graphically marked on the image, and the total count of coins is displayed. We also provide a feature to save the processed image with the marked coins. This interactive tool seamlessly combines image processing techniques with an intuitive interface, making it easy even for non-experts to count coins in images. Here we're defining a new function named processImage, which will take in an image and a series of parameters designed to help us detect coins within that image.
We start by converting our input image from color to grayscale, which simplifies processing since we no longer need to deal with color channels.
Next, we apply Gaussian blur to the grayscale image using a kernel size we specify, helping to reduce noise and detail that might interfere with coin detection. We convert the blurred image to a binary image by thresholding it, which helps differentiate coins from the background by turning them into distinct black and white areas. We create a kernel, a small matrix which will be used for erosion, a process that helps enhance the areas of interest within our binary image. Using the kernel we created, we erode the binary image to remove small noise and detach slightly connected components, iterating the process the specified number of times. After erosion, we apply another Gaussian blur to the image to further smooth it out and prepare it for final thresholding. Finally, we apply a second threshold to the eroded and blurred image to obtain a clear silhouette of the coins against the background. Here, we identify and label connected components in the thresholded image, which are potential coin candidates, by assigning unique labels to each connected region. We filter out small components by checking their contour areas, keeping only those larger than a certain size, which we assume to be actual coins. We make a copy of the original image, which we'll use to draw detected coins for a visual output. We loop through each of the detected coin labels to mark their locations on the copied image. For each coin label, we find all coordinate points belonging to that component in the labeled image. We loop through each coordinate to draw marks on those detected coin positions. We draw a small green circle at each detected coin position to visually indicate where each coin is located in the output image. We count the number of unique coin labels, which gives us the total number of detected coins in the image. Finally, we return both the marked output image and the total count of detected coins from our function.
Next, we're defining another function named selectImage to handle the user's image selection process.
We open a file dialog to prompt the user to select an image file for processing.
We check whether the user has selected a file or canceled the dialog.
If no file was selected, we pop up an error message asking the user to select an image file to proceed. We terminate the function early if no image was selected, preventing further processing on a non-existent file. Here we're fetching the current value from the blur slider, which will determine how much the image will be blurred.
Next, we grab the value from the threshold slider, essential for distinguishing the coins from the background in the image.
We also get the number of erosion iterations from the erosion slider, which will help in refining the contours of the coins. Finally, we collect the value from the final threshold slider, which is used to further process the image after initial thresholding. Here we ensure that the blur kernel size is an odd number since even numbers aren't valid for this operation. If the blur kernel size is even, we simply add 1 to make it odd. We declare processed image as a global variable, so it can be accessed outside this function. We process the image using the processImage function and receive a blurred and thresholded version of the image, along with the number of detected coins. Ensuring the processed image is valid, we proceed with further actions. We display the processed image in a window titled Coin Counter. Now, with this command, we close all OpenCV windows that were opened. A message box pops up displaying the number of coins that were detected in the processed image. Here we define a new function SaveResults to save the processed image to a file. This condition checks if a processed image exists before allowing a save operation. If no processed image is available, we alert the user with an error message. We exit the function if there is no image to save. Prompts the user with a Save As dialog to choose where to save the processed image, with .png as the default extension. After the file path is obtained, we check if the user indeed selected a location to save the file. We save the processed image to the specified path using OpenCV's imWrite function. Once saved, a confirmation message box appears, informing the user that the image has been saved successfully. We initialize the main application window using the tkinter library. We set the title of the application window to Coin Counter, giving some context to what the app does. The dimensions of the application window are set to 300 pixels in width and 450 pixels in height. A label widget is created to explain the purpose of the blur slider to the user. This places the blur label within the app window and gives it some vertical space with padding. We set up a slider to choose the blur kernel size, ranging from 3 to 31, increasing by 2 to ensure only odd numbers. Initially, the slider is set to a value of 5 to give a default starting point for the blur. Finally, we pack the slider into the app window, again providing some vertical space around it. Here we're creating a label widget in our app window to display the text threshold value, which helps the user understand what the slider below is for. Next, we're adding this label widget to our app window and giving it some vertical padding of 5 pixels for better spacing.
Now we're adding a horizontal slider widget called Threshold Slider to our app, which lets the user select a threshold value between 1 and 255.
We're setting the default value of our threshold slider to 50, so it starts at this midpoint when the app launches. Just like the label, we're adding the threshold slider to our app and giving it some vertical padding of 5 pixels. Creating another label widget, this time to inform the user about the erosion iterations slider below, which controls the number of erosion operations. Adding the erosion label to our app with a 5-pixel vertical padding for spacing.
We're adding another horizontal slider called Erosion Slider that lets users choose how many iterations of erosion to apply within the range of 1 to 10.
This time we're setting the default value of the erosion slider to 5, so it comes pre-configured at a middle value. The erosion slider is then placed in the app window with a 5-pixel vertical padding. We create a third label widget to describe the purpose of the final threshold value slider, giving users a hint about its function. This label is packed into the app window with a 5-pixel vertical padding for spacing. We're adding another slider called Final Threshold Slider, allowing users to select a final threshold value between 1 and 255 as a fine-tuning step. Setting the initial value of the final threshold slider to 225, providing a default position towards the higher end of the range. We pack the final threshold slider into the app window with a 5-pixel padding to enhance layout aesthetics. Creating a button widget labeled Select Image, which when clicked, will execute the Select Image function, allowing users to choose an image to work with. This button is added to our app with a bit more padding, 10 pixels, for more prominent spacing and visual separation. Another button widget is created and labeled Save Results. It runs the Save Results function when pressed, letting users save their processed data. Just like the Select Image button, we add this Save Results button to the app window with a 10-pixel padding for appropriate spacing. Finally, we use App Main Loop to start the main loop of our application, which keeps the window open and responsive to user interactions.
In this project, we will develop a face-swapping application using Python that leverages computer vision and image processing techniques. The application utilizes the OpenCV library for reading and manipulating images, dlib for detecting facial landmarks, and tkinter for creating a graphical user interface. Users can select 2 images containing faces, and the program will detect facial landmarks to compute the required transformations for swapping the faces between the images while maintaining natural appearances using color correction and seamless cloning techniques. Featuring multi-threading to ensure a responsive GUI, users can visualize the original and modified images side by side and have the option to save the swapped images to their local storage.
We're creating a face detector object using dlib's frontal face detector, which will help us find faces in our images.
Now we're initializing a shape predictor using a pre-trained model file, which will allow us to detect facial landmarks on the faces we find.
We're setting up an empty string variable to store the file path of our first image, which we'll use later when we load the image. Similarly, we're creating another empty string variable for the file path of our second image. We're initializing a variable called panel A as none, which we'll use later to display our first image in the GUI. We're doing the same for panel B, which will be used to show our second image, and again for panel C, which will display the result of our face swapping process.
We're setting up a variable called root as none, which will later hold our main application window.
We're initializing a progress bar variable as none, which we'll use to show the progress of our face swapping operation. We're creating a Boolean flag called isProcessing and setting it to false, which we'll use to keep track of whether our script is currently processing images or not. We're defining a function called getLandmarks that takes an image as input and will return the facial landmarks for that image. Inside our function, we're converting the input image to grayscale, which is often necessary for face detection algorithms. We're using our face detector to find any faces in the grayscale image. We're checking if any faces were found in the image. If no faces were found, we're returning none to indicate that landmarks couldn't be detected. If a face was found, we're using our shape predictor to get the facial landmarks and returning them as a NumPy matrix. We're defining a new function called transformation from points that will calculate the transformation between 2 sets of points. We're converting the first set of points to 64-bit float type for more precise calculations. We're doing the same conversion for the second set of points. We're calculating the mean center of the first set of points. We're doing the same for the second set of points. We're centering the first set of points by subtracting their mean. We're centering the second set of points in the same way. We're calculating the standard deviation of the first set of points. We're doing the same for the second set of points. We're normalizing the first set of points by dividing by their standard deviation. We're normalizing the second set of points in the same way. We're using singular value decomposition, SVD, to find the optimal rotation between the 2 sets of points. We're calculating the rotation matrix from the SVD results. We're constructing the full transformation matrix, including scaling, rotation, and translation. We're returning the calculated transformation matrix. We're defining a function called warp image that will apply a transformation to an image. We're using OpenCV's warp affine function to apply our transformation to the image, using reflection to handle areas outside the image boundaries.
We're returning the warped, transformed image. We're defining a function called correct colors that takes two images and facial landmarks as input to adjust the colors of the swapped face.
Here, we're calculating the blur amount based on the distance between the eyes and the facial landmarks to determine how much we should blur the images. We're converting the blur amount to an integer to use it as a parameter for the Gaussian blur function. We're checking if the blur amount is even because Gaussian blur requires an odd kernel size.
If the blur amount is even, we're adding 1 to make it odd.
We're applying Gaussian blur to the first image using the calculated blur amount. We're applying the same Gaussian blur to the second image. We're combining the images and their blurred versions to correct the colors, clipping the values between 0 and 255, and returning the result as an 8-bit unsigned integer image. We're defining a function to select an image file with a parameter to determine if it's the first or second image being selected. We're declaring these variables as global so we can modify them within the function. We're opening a file dialog for the user to select an image file. We're checking if a file was actually selected by the user. We're reading the selected image and converting its color space from BGR to RGB. We're converting the NumPy array to a PIL image object. We're creating a tkinter-compatible photo image from the PIL image. We're checking if this is the first image being selected. If it's the first image, we're storing its path in the global variable imagePath A. We're checking if the first image panel doesn't exist yet. If the panel doesn't exist, we're creating a new label widget to display the image. We're storing a reference to the image to prevent it from being garbage collected. We're adding the image panel to the GUI positioned on the left side with some padding. If the first image panel already exists, we're updating it with the new image.
We're updating the existing panel with the new image.
We're updating the image reference to prevent garbage collection. If it's not the first image, we're handling the second image selection. We're storing the path of the second image in the global variable imagePath B. We're checking if the second image panel doesn't exist yet. If it doesn't exist, we're creating a new label widget for the second image. We're storing a reference to the second image to prevent garbage collection. We're adding the second image panel to the GUI, positioned on the right side with padding. If the second image panel already exists, we're updating it. We're updating the existing second panel with the new image. We're updating the image reference for the second panel. We're defining a function to run the face swapping process in a separate thread. We're declaring isProcessing as global so we can modify it within the function. We're setting the processing flag to true to indicate that face swapping is in progress. We're starting the progress bar animation with an interval of 10 milliseconds. We're calling the main face swapping function to perform the actual face swap. We're stopping the progress bar animation once the face swapping is complete. We're setting the processing flag back to false to indicate that face swapping is finished. We're defining the main function that performs the face swapping operation.
We're declaring panel C as global so we can modify it within the function.
We're checking if both images have been selected before proceeding with the face swap. We display an error message to the user if they haven't selected both images yet, ensuring we have the necessary input before proceeding. We exit the function early if the images aren't selected, preventing any further processing. Here we're loading the first image from the file path using OpenCV's imread function, which gives us the image data to work with. Similarly, we load the second image using the same method, preparing both images for processing. We call a function to detect facial landmarks in the first image, which will help us locate and manipulate the face. We do the same for the second image, getting the facial landmarks that we'll need for the face swap. We check if facial landmarks were successfully detected in both images, as we can't proceed without them. If landmarks aren't found, we show an error message to the user, explaining the issue and suggesting possible solutions. We exit the function if landmarks aren't found, as we can't continue the face swap process without them. We calculate the bounding rectangle for the face in the first image based on its landmarks, giving us the position and size of the face. We do the same for the second image, getting the bounding rectangle for that face as well. We calculate the center point of the first face's bounding rectangle, which we'll use later for positioning. Similarly, we find the center point of the second face's bounding rectangle. We compute the transformation needed to map the landmarks of the first face onto the second face. We apply this transformation to warp the second image to match the shape of the first face. We adjust the colors of the warped image to better match the first image, improving the blend. We create a blank mask the same size as the first image, which we'll use to define the face region. We fill in the mask with white in the region defined by the convex hull of the face landmarks, creating a face-shaped mask. We use OpenCV's seamless cloning to blend the warped face into the first image at the calculated center point, creating a natural-looking swap.
Now we repeat the process for the second face, starting with computing the reverse transformation.
We warp the first image to match the shape of the second face. We correct the colors of this warped image to match the second image. We create another blank mask, this time for the second image. We fill in this mask with the face shape from the second image's landmarks. We perform the seamless cloning again, this time blending the first face onto the second image. We combine both face-swapped images side by side into a single output image. We convert the color space of our output image from BGR, OpenCV's default, to RGB for proper display. We convert our NumPy array to a PIL image object, which is compatible with tkinter. Finally, we convert the PIL image to a tkinter-compatible photo image, ready for display in our GUI. We check if we've already created a panel for displaying our output image, so we know whether to create a new one or update the existing one.
We're creating a new label widget called Panel C, which will be used to display our output image in the main window. Now we're positioning the Panel C label at the bottom of our window, making it fill both horizontally and vertically, and adding some padding for a nicer look.
Here we're setting the image of our Panel C label to be the output image, which is the result of our face swapping operation. This line is important for keeping a reference to our output image, preventing it from being garbage collected by Python. We're defining a new function called saveImage, which will handle saving our face-swapped image to a file. This is a safety check to make sure we actually have an image to save before proceeding. If there's no image to save, we show an error message to the user asking them to swap faces first. We exit the saveImage function early if there's no image to save. This opens a file dialog for the user to choose where to save the image, defaulting to a PNG file. We check if the user actually selected a file path and didn't cancel the save operation. We convert the photo image object back to a PIL image object so we can save it. Now we save the image to the file path the user selected. We show a success message to the user, confirming that the image was saved and where. This function will set up our entire graphical user interface. We're declaring these variables as global so we can access them throughout our script. This creates the main window of our application. We're setting the title of our main window to Face Swapper. We're creating a main frame to hold all our widgets. We're adding the main frame to our window with some padding. This creates a new frame specifically for our buttons. We're positioning the buttons frame at the top of our main frame and making it fill horizontally. This creates our first button for selecting an image, which we'll call SelectImage True when clicked. We're positioning our first button on the left side of the button's frame with some horizontal padding. This creates our second button for selecting an image, which we'll call SelectImage False when clicked. We're positioning our second button to the right of the first button with some horizontal padding. This creates our Swap Faces button, which starts a new thread to run the face swapping process when clicked. We're positioning our Swap Faces button to the right of the second button with some horizontal padding. This creates our Save Image button, which we'll call the Save Image function when clicked. We're positioning our Save Image button at the top of the main frame, making it fill horizontally, and adding some vertical padding. This creates a horizontal progress bar that will show indeterminate progress during the face swapping process. We're positioning our progress bar at the top of the main frame, making it fill horizontally, and adding some vertical padding. Finally, we start the main event loop of our application, which will keep our window open and responsive to user interactions. This line checks if the script is being run directly as the main program, ensuring that the code inside this block only executes when the script is run directly and not when it's imported as a module. This line calls the createGuy function, which likely sets up and displays the graphical user interface for our application making it visible and interactive for the user. In this project, we will develop an advanced face detection app using Python, leveraging libraries such as OpenCV, tkinter, and PIL. This application provides a user-friendly interface for detecting faces in both images and videos. Users can seamlessly upload images or connect to video sources for real-time face detection. The app is structured into 3 main tabs: image processing for static images, video processing for live video feeds, and settings for configuring parameters like scale factor, minimum neighbors, and minimum size required for face detection. The software employs Hough cascade classifier for facial recognition and allows for customization and saving of user-preferred settings. Built with multi-threading capabilities, the app efficiently handles video processing tasks in the background, ensuring smooth user interaction. We're defining a new class called Face Detection App, which will contain all the methods and attributes for our face detection application. This is the constructor method for our Face Detection App class, which initializes the app with a root window passed as an argument. We're storing the root window as an instance variable so we can use it throughout the class. Here we're setting the title of our application window to Advanced Face Detection App. We're setting the initial size of our application window to 800 pixels wide by 900 pixels tall. We're creating a TTK-style object to customize the appearance of our widgets. We're setting the theme of our application to clam, which gives it a modern look. We're creating a notebook widget, which allows us to have multiple tabs in our application.
We're adding the notebook to our window, making it fill the entire space and expand as needed.
We're creating a frame widget for our image processing tab. We're creating another frame widget, this time for our video processing tab. We're creating a third frame widget for our settings tab. We're adding the image processing tab to our notebook with the label image processing.
We're adding the video processing tab to our notebook, labeling it video processing.
We're adding the settings tab to our notebook with the label settings. We're calling a method to set up the components of our image processing tab. We're calling a method to set up the components of our video processing tab. We're calling a method to set up the components of our settings tab. We're initializing an instance variable to store the currently loaded image, setting it to none for now. We're initializing an instance variable to store the video capture object, setting it to none initially. We're creating a Boolean flag to keep track of whether we're currently processing a video.
We're loading the Hough cascade classifier for face detection from OpenCV's pre-trained models.
We're calling a method to load any saved settings for our application. We're defining a method to set up the components of our image processing tab.
We're creating a button labeled Upload Image that will trigger the Upload Image method when clicked.
We're adding the Upload button to our image tab with some vertical padding. We're creating a Detect Faces button that will be initially disabled and will call the Detect Faces method when clicked. We're adding the Detect Faces button to our image tab with some vertical padding. We're creating a Save Image button that will be initially disabled and will call the Save Image method when clicked.
We're adding some vertical padding to our Save button to give it some space from other elements.
Here we're creating a label widget in our Image tab to display the processed image. We're packing our display label and allowing it to expand to fill available space in the Image tab.
Now we're defining a method to set up the video processing tab of our application.
We're creating a string var to hold the video source, defaulting to 0, which typically represents the default camera. Here, we're creating an entry widget for the user to input the video source, linked to our video source variable. We're adding our video source entry to the layout with some vertical padding. Now we're creating a button that will start the video processing when clicked. We're adding our Start Video button to the layout with some vertical padding. Here we're creating a button to stop video processing, initially disabled as we haven't started processing yet. We're adding our Stop Video button to the layout with some vertical padding.
We're creating a label widget in our Video tab to display the processed video frames.
We're packing our video label and allowing it to expand to fill available space in the Video tab.
Now we're defining a method to set up the Settings tab of our application. We're creating a double var to hold the scale factor for face detection, with a default value of 1.1.
Here we're creating an int var to hold the minimum neighbors parameter for face detection, defaulting to 5. We're creating another int var to hold the minimum size for detected faces, with a default of 30 pixels.
Now we're adding a label for the scale factor setting to our grid layout.
We're creating an entry widget for the scale factor, linked to our scale factor variable, and adding it to the grid. Here we're adding a label for the minimum neighbors setting to our grid layout. We're creating an entry widget for the minimum neighbors, linked to our min neighbors variable, and adding it to the grid.
Now we're adding a label for the minimum size setting to our grid layout.
We're creating an entry widget for the minimum size, linked to our min size variable, and adding it to the grid.
Here we're adding a button to save the settings, which will span 2 columns in our grid layout. Now we're defining a method to handle image uploading in our application.
We're opening a file dialog for the user to select an image file, restricting the file types to common image formats. Here we're checking if a file was actually selected by the user. If a file was selected, we're reading the image using OpenCV and storing it in our image attribute. Now we're calling a method to display the uploaded image in our application.
Finally, we're enabling the detect button now that we have an image uploaded.
Here we're defining a method to handle face detection in our uploaded image. We're checking if an image has been uploaded before attempting face detection. We're converting our input image to grayscale using OpenCV's CVT color function, which helps simplify face detection by reducing the image to a single channel.
Now we're using our cascade classifier to detect faces in the grayscale image, with parameters that we can adjust to fine-tune the detection process.
We're starting a loop that goes through each detected face, where x and y are the top left coordinates, and w and h are the width and height of the face rectangle. Here we're drawing a blue rectangle around each detected face on our original image using OpenCV's rectangle function. We're calling our showImage method to display the processed image with face rectangles on the GUI. We're enabling the Save button now that we have a processed image to save. In our showImage method, we're converting the image from BGR to RGB color space, which is necessary for displaying it correctly in tkinter. We're creating a PIL image object from our RGB numpy array, which is a step in converting our OpenCV image to a format tkinter can display. Now we're creating a tkinter compatible photo image from our PIL image. We're storing our tkinter photo image as an attribute of the display label to prevent it from being garbage collected.
We're updating our display label with the new image, which will show it in our GUI.
In our SaveImage method, we're first checking if there's actually an image to save. We're checking if the user actually selected a file path and didn't cancel the save operation.
We're using OpenCV to write our image to the file path the user selected.
In our Start Video Processing method, we're starting a try except block to handle potential errors when getting the video source. We're trying to convert the video source to an integer, which would represent a camera index. If the conversion to int fails, we catch the value error exception. If it's not an integer, we assume it's a string representing a video file path. We're creating a video capture object to start capturing video from the specified source. We're checking if the video capture was successful and the video source is opened. We're setting a flag to indicate that video processing has started. We're disabling the Start Video button to prevent starting multiple video processes. We're enabling the Stop Video button so the user can stop the video processing. We're starting a new thread to run our video processing function, allowing the GUI to remain responsive during processing.
We're setting the eyes processing video flag to false, indicating that we've stopped processing the video.
Here we're checking if there's an active video capture object. If there is an active video capture, we're releasing it to free up system resources. Now we're enabling the Start Video button so the user can start a new video capture. We're disabling the Stop Video button since we've already stopped the video processing. This function defines the main video processing loop where we'll detect faces in each frame. We start a loop that continues as long as we're supposed to be processing video. We'll use a try-except block to handle potential errors when loading the settings file. Here we're reading a frame from the video capture. Ret tells us if it was successful, and frame contains the actual image data. We're checking if we failed to read a frame, which could mean we've reached the end of the video. We're converting the color frame to grayscale, which is typically used for face detection algorithms.
Now we're using our cascade classifier to detect faces in the grayscale image, with parameters we've set earlier.
We're starting a loop to process each detected face, where x and y are the top left corner coordinates, and w and h are the width and height of the face rectangle. For each face, we're drawing a blue rectangle around it on the original frame. We're calling a function to display the processed frame with face rectangles drawn on it. After the video processing loop ends, we're clearing the video display by setting its image to none. This function is responsible for displaying a single video frame in our GUI.
We're converting the frame from BGR, OpenCV's default, to RGB color space for proper display.
Now we're creating a PIL image object from our RGB numpy array. We're creating a tkinter-compatible image object from our PIL image. We're storing a reference to our tkinter image to prevent it from being garbage collected. Finally, we're updating our video label with the new frame image. This function is responsible for saving our current face detection settings. We're creating a dictionary to store our current settings values. We're opening a JSON file in write mode to save our settings. Lastly, we're writing our settings dictionary to the JSON file in a formatted manner. We're displaying a success message to the user, confirming that their settings have been saved successfully.
Now, let's define a method called loadSettings that will handle loading previously saved settings for our face detection application. We'll use a try-except block to handle potential errors when loading the settings file. Here we're opening our settings file named facedetectionsettings.json in read mode, which will allow us to access its contents. We're using the json.load function to parse the contents of our settings file and store the resulting dictionary in a variable called settings. Now we're setting the scale factor value in our application, using the value from our settings file if it exists, or defaulting to 1.1 if it doesn't.
Similarly, we're setting the minimum neighbors value, either from our settings file or using the default value of 5. And lastly, we're setting the minimum size value, again either from our settings file or using the default value of 30. If we encounter a file not found error, which would happen if the settings file doesn't exist, we'll handle it in this except block. In case of a file not found error, we're simply passing, which means we'll do nothing and continue with the program execution. Let's define our main function, which will serve as the entry point for our face detection application. We're creating the root window for our tkinter application, which will contain all our GUI elements.
Now we're creating an instance of our face detection app class, passing in the root window we just created.
Finally, we're starting the main event loop of our tkinter application, which will keep our GUI responsive and handle user interactions.
This condition checks if our script is being run directly, not imported as a module.
If the script is run directly, we call our main function to start the face detection application. In this project, we will create a Python application using OpenCV and tkinter that allows users to transform their images into cartoon-like versions. The application features a graphical user interface where users can open and process individual images or perform batch processing on multiple images. Users can adjust parameters such as blur level, block size, and bilateral filter values to customize the cartoonification effect. The cartoonified images are saved to a specified directory, and the operation details are logged in a JSON file. Additionally, users can view a log of all operations performed, making it easy to keep track of processed images. This tool combines image processing capabilities with a user-friendly interface, enabling creative and efficient image transformation. We're defining a function named cartoonifyImage, which takes an image and optional parameters to control the cartoonifying process. We check if the blur value is an even number to ensure its effectiveness in the blurring process. If blur value was even, we make it odd by adding 1 because blurring works better with odd numbers. Next, we want to ensure that blur value is at least 1 because 0 or negative values don't make sense for blurring. If the blur value is less than 1, we set it to 1 as a sensible default. Similarly, we check if block size is an even number because thresholding requires it to be odd. If block size is even, we increment it by 1 to make it odd. We check if block size is less than or equal to 1, since our thresholding utility requires a minimum size. We convert the input image to grayscale because edge detection works better on single-channel images. We apply a median blur to the grayscale image using blur value, which helps in reducing noise.
Next, we detect edges in the blurred grayscale image using adaptive thresholding, an essential step for cartoonifying.
We smoothen the original image using a bilateral filter to preserve edges while reducing color noise. We combine the edge-detected mask and the smoothed color image to produce a cartoon-like effect. Finally, we return the cartoonified image as the output of the function. Here's a function named OpenFile that will help us select and process a single image file. We display a file dialog to choose an image from disk, filtering by common image formats. We check if a file was actually selected to avoid processing a non-existent file. Once a file is selected, we read the image using OpenCV's imread function. We call another function to adjust settings and process the image, leveraging the file path for storage or further use. We set up a new function, process multiple files, to handle processing multiple images in one go. We use a dialog to select multiple image files simultaneously, allowing for batch processing. Here we verify if any files were selected before proceeding to avoid errors. We loop through each of the selected file paths to handle them individually. For each file, we read the image data into our program using OpenCV. We apply our earlier cartoonifyImage function to transform each image into its cartoon version. We save the cartoonified image alongside the original one to easily store and identify the output. After processing all images, we show a message box to tell the user that everything's done and saved. Here we're defining a function called saveCartoon, which will take in 2 arguments, the cartoon image and the path of the original image. We set savedir to be the directory named cartoonified images, where we'll store our cartoon versions of images. We're checking if the directory savedir doesn't already exist on the file system. If savedir doesn't exist, we create it using os-makeDirs, so that we have a place to save our cartoon images. We extract the file name from original path using os.path.basename and store it in basename. We construct savePath by joining our savedir with a new name that includes cartoonified and the original file name. We save the cartoon image to savePath using cv2.imwrite so that it gets written to disk. Next, we call logoperation to log the action we just performed by passing in original path and savePath. We show a message box to inform the user that the cartoon image has been successfully saved to savePath. Now we define the logoperation function, which logs the original and output paths to a JSON file. We set logFile to operationlog.json, which will store our operation logs. We initialize log data as an empty list to store our log entries. We check if logFile already exists in the file system to decide if we need to load existing logs. If logFile exists, we open it in read mode so that we can load the existing data. We load the content of logFile into log data using json.load if the file exists. We add a new dictionary containing our input path and output path to log data. We open logFile in write mode to update it with the new log data. We write log data back to logFile in a nicely formatted JSON structure with indent folder. Here we define another function, viewLogs, specifically to display the logs to the user. We refer back to our log file where all the logs are stored as before. We check if the log file does not exist, which means there are no logs to display. If the log file is missing, we show a warning message informing the user that no logs are available. Otherwise, we open log file in read mode to access the log data. We load the contents of log file into logs to display it to the user. We create a new top-level window titled Log Window to display the logs using the tkinter library. We set the title of log window to Operation Logs to reflect its content. We create a text widget inside log window for displaying log text with word wrapping and specified dimensions. We loop over each log entry in our logs variable to display them in the text widget. For each log entry, we insert a formatted string with input and output paths, followed by 2 new lines into the text widget. We disable the log text widget to prevent user edits after inserting log entries. We pack the log text widget within the window with some padding around it for a clean appearance. We create a button widget labeled Close, which will destroy close, the log window when clicked. We pack the close button into the window with some vertical padding to separate it from other elements. We're defining a new function called adjust parameters and process that will take in 2 arguments: image for the image we want to process, and file path where we might save the result. Here we're creating a new top-level window using tkinter, which will be a separate window from our main application, to allow users to adjust image processing parameters. Next, we're setting the title of our new window to Adjust Parameters, so users know their current task is to tweak settings. We're adding a label to our parameters window to prompt the user to select a blur value, and we're positioning it in the grid at row 0, column 0, with some padding around it. We create a scale widget for the user to select a blur value, specifying a range from 1 to 15 and displaying it horizontally to modify the blur effect on the image. We set the default starting value of the blur scale to 5, so users have a middle ground starting point for adjustments. We position the blur scale in the grid next to the blur label at row 0, column 1, maintaining the consistent padding. A new label is created to guide the user in selecting a block size, appearing just below the blur label, to further refine the cartoon effect. We introduce another scale for block size, with the same range and orientation as the blur scale, for adjusting the detail level in the image. We initialize this block size scale to 9, providing a reasonable default which balances detail and simplicity. We place the block size slider right beside its label at row 1, column 1 with some padding, keeping the layout neat. Another label is placed to inform users about the bilateral filter setting, located under the previous controls, affecting edge smoothing in the image. This scale lets users choose a bilateral filter value between 100 and 500, helpful for tweaking how smooth the image's colors appear. We set a default bilateral filter scale value of 250, offering a moderate level of smoothness in the image processing. We slot the bilateral filter scale into the grid beside its label at row 2, column 1, with matching padding, keeping the user interface uniform. We're defining a nested function named Process with Parameters that will process the image with the user's chosen parameters. Inside this function, we call a Cartoonify image utility, feeding it the current image and the user's selected parameters, and store the result as cartoon. Next, we pass our cartoonified image to a function that displays the cartoon to the user for previewing. A message box pops up with a yes/no question, asking if the user wants to save the cartoonified image they just previewed. We check if the user chose yes to saving the image. If they did decide to save, we call a save cartoon function with the cartoon image and the specified file path to store it. We create a button labeled Process Image, which when clicked, will execute our Process with Parameters function. Finally, we add this button to the Parameters window grid, spanning 2 columns at row 3, with some vertical padding to separate it from the controls. We're defining another function named DisplayCartoon, which will handle showing the cartoonified image in a separate window. Inside, we convert the cartoon from BGR, used by OpenCV, to RGB color space, better for display, and assign it to Cartoon RGB. We then convert this RGB image into a pill image object named Cartoon Pill, making it ready for visualization using tkinter. We further convert Cartoon Pill into a photo image object compatible with tkinter, storing it as Cartoon TK to enable GUI display. A new preview window is created to display the cartoonified image, separate from the main and parameter windows. We give the preview window a title of Cartoonified Preview, ensuring users know what they're viewing. Inside, we create a label widget holding our cartoon image to display it within the new window. We pack our label into the window, which effectively arranges it to fill the window based on default rules.
We add a close button that, when pressed, will destroy the preview window, closing it neatly for the user.
This button is packed below the image with some padding to maintain a tidy appearance within the preview window. Finally, we're defining the main function, which will set up and start the tkinter graphical user interface, GUI, for our application.
Within the main function, we first create the main application window using tkinter, calling it root. We set the title of this main window to Cartoonify Image, giving users a clear idea of the app's purpose upon launch. Here we're creating a new label widget using tkinter, assigning it to the variable label, setting its parent container to root, and displaying the text, Cartoonification of Images, with the font style Arial at font size 18.
This line positions the label in the window using the Pack Geometry Manager, adding 20 pixels of vertical padding, patty, around it for spacing.
Now we create a button widget named OpenButton, which will be placed inside root, labeled with the text OpenImage, set to call the OpenFile function when clicked, and sized with a height of 2 units and a width of 20 units.
We use Pack again to position the Open button and add 10 pixels of vertical padding around it for spacing from other elements. This instruction constructs another button widget called Batch Button, parented to root, labeled Batch Process Images, designed to invoke the Process Multiple Files function when clicked, and styled with a height of 2 and width of 20. The Batch button is placed using Pack with 10 pixels of vertical padding to separate it from neighboring widgets.
Here we add a new button widget titled Log Button, which resides in root, shows the label View Logs, runs the View Logs function on click, and is shaped with a height of 2 and width of 20.
We arrange the Log button on the window using Pack, providing 10 pixels of vertical padding space for a neat look. We define another label, Footer Label, in root, setting its text to Created with OpenCV and tkinter, using Arial font at size 8, with text color in gray. The footer label is positioned using Pack, with 10 pixels of vertical space around it at the bottom of the window for clear separation. Finally, we call root.mainLoop, which enters the tkinter event loop that waits for any event to occur in the UI, like button clicks, keeping the application running and responsive.
This condition checks if the Python file is being run as the main program, ensuring the subsequent code block runs only in this scenario.
Within this block, we invoke main, signaling the start of our main application functionality. In this project, we will develop an advanced image processing tool using Python, combining the capabilities of OpenCV, NumPy, and a user-friendly GUI built with tkinter. The application is designed to allow users to perform a variety of image processing tasks through an intuitive interface. Users can load and save images, apply transformations like histogram equalization, Gaussian and median blurring, edge detection, and sharpening. It also includes functions for adjusting image brightness and contrast with real-time previews of modifications. The tool maintains a history of processing steps, enabling users to undo changes or reset to the original image. Furthermore, users can visualize the image's histogram, providing insight into the distribution of intensity within their pictures. We're defining a new class called Advanced Image Processing App, which will contain all the functionality for our image processing application. This is the constructor method for our class, which initializes the application with a root window passed as an argument. We're storing the root window as an instance variable so we can use it throughout the class. Here, we're setting the title of our application window to Advanced Image Processing Tool. We're setting the initial size of our application window to 1200 pixels wide by 800 pixels tall.
We're initializing an instance variable to store the path of the loaded image, starting with none since no image is loaded yet.
This instance variable will store the original loaded image, initially set to none. Here we're creating an instance variable to store the processed version of the image, starting with none. We're initializing an empty list to keep track of the processing steps applied to the image. This line calls the createGuy method, which will set up the graphical user interface for our application. We're defining the createGuy method, which will contain all the code for setting up the application's user interface. Here we're creating the main frame of our application with some padding around it. We're using the Grid Layout Manager to position our main frame and make it expand in all directions. This line configures the root window's first column to expand horizontally. Similarly, we're configuring the root window's first row to expand vertically. We're creating a control frame within the main frame to hold our buttons and controls. Here we're positioning the control frame at the top of the main frame and making it expand horizontally. We're creating a button labeled Load Image that will call the Load Image method when clicked. This line positions the load button in the control frame with some padding around it. We're creating a Save Image button that will call the Save Image method when clicked. Here we're positioning the Save button next to the Load button in the control frame. We're creating a button for histogram equalization, which will call the Equalize Histogram method when clicked. This line positions the Equalize Histogram button next to the Save button in the control frame. We're creating a button for applying Gaussian blur, which will call the Gaussian blur method when clicked.
Here we're positioning the Gaussian blur button on the second row of the control frame.
Finally, we're creating a button for applying median blur, which will call the median blur method when clicked. We're placing the median blur button in the grid layout at row 1, column 1, with some padding to give it a bit of space around it. Here we're creating a new button labeled Sharpen that will call the Sharpen function when clicked.
Now we're positioning the Sharpen button in our grid, right next to the median blur button, with some padding for spacing.
We're creating another button, this time for edge detection, which will trigger the edge detection function when pressed.
Let's place the edge detection button in the grid, next to our Sharpen button, completing our row of image processing options.
We're setting up a new frame within our control area to house the brightness adjustment controls.
Now we're positioning the brightness frame in the grid, spanning 2 columns to give it more space.
We're adding a label next to our brightness control, packing it to the left side of the frame.
Here we're creating a slider for brightness adjustment, setting its range from 100 to 100, and linking it to our brightness adjustment function.
We're setting the initial value of our brightness slider to 0, which represents no change in brightness.
Now we're adding our brightness slider to the frame, positioning it to the left of any remaining space.
Similar to brightness, we're creating a new frame for our contrast controls. We're positioning the contrast frame in the grid, right next to our brightness frame, adding a label for our contrast control, packing it to the left side of the frame.
Now we're creating the contrast slider, setting its range from 0.5 to 2.0, and linking it to our contrast adjustment function.
We're setting the initial value of our contrast slider to 1.0, which represents no change in contrast. Adding our contrast slider to the frame, positioning it to the left of any remaining space. We're creating an undo button that will revert the last change when clicked, positioning our undo button in the grid, starting a new row of controls. Creating a reset button that will restore the image to its original state when clicked, placing the reset button in our grid, leaving a space between it and the undo button. We're adding a button that will display the image histogram when clicked, positioning our histogram button in the grid, completing our row of utility buttons. We're creating a frame to hold our image display, giving it a sunken appearance with a border, positioning our image frame below the controls, spanning the full width of the window, and expanding to fill available space, creating a label within our image frame where we'll display the actual image. We're packing our image label to expand and fill the entire image frame, ensuring the image can be as large as possible.
Now we're defining the load image function, which will handle opening and displaying a new image file.
We're opening a file dialog for the user to select an image file, specifying the types of image files that can be chosen. We're checking if a file path was selected by the user, which determines our next steps. We're storing the selected file path in our object's image path attribute for future reference. We're using OpenCV to read the image from the selected file path and store it as our original image. We're creating a copy of the original image to work on, so we can modify it without affecting the original. We're initializing our processing history with a copy of the original image, allowing us to track changes. We're calling our displayImage method to show the newly loaded image in the GUI. If no file path was selected, we're showing an info message to the user. We're checking if there's a processed image available before attempting to save it. We're checking if the user actually selected a save location. We're using OpenCV to write our processed image to the selected file path. We're showing a success message with the save location after the image is saved. If there's no processed image, we're showing a warning message to the user. We're converting the image from BGR to RGB color space for proper display. We're creating a PIL image object from our RGB image array. We're creating a tkinter compatible photo image from our PIL image. We're updating our image label in the GUI with the new image. We're keeping a reference to the image to prevent it from being garbage collected. We're checking if there's a processed image before applying histogram equalization. We're converting the image to grayscale, which is required for histogram equalization. We're applying histogram equalization to improve the contrast of our grayscale image. We're converting the equalized image back to BGR color space and updating our processed image. We're updating our processing history to include this new change. We're displaying the newly equalized image in our GUI. If there's no processed image, we're showing a warning message to the user. We're checking if there's a processed image before applying Gaussian blur.
We're applying Gaussian blur to our image with a 5x5 kernel to reduce noise and smooth the image.
We're updating our processing history to include this new change. We're displaying the newly blurred image in our GUI. If there's no processed image, we're showing a warning message to the user. We're checking if there's a processed image before applying median blur. We're applying a median blur filter to our processed image with a kernel size of 5, which helps reduce noise while preserving edges. Now we're updating our processing history to keep track of the changes we've made to the image. Let's display the updated image on our interface so we can see the results of the blur filter. We're displaying a warning message box to inform the user that they need to load an image before applying filters.
Here we're defining a new method called sharpen that will apply a sharpening filter to our image.
We're checking if there's an image loaded before proceeding with the sharpening process. We're creating a 3x3 kernel array that defines our sharpening filter.
Now we're applying the sharpening filter to our image using OpenCV's filter2D function.
We're updating our processing history to include the sharpening operation. Let's display the sharpened image on our interface. This line displays a warning message box to the user, informing them that no image has been loaded yet. We're defining a new method for edge detection, which will highlight the edges in our image. We're checking if there's an image loaded before proceeding with the sharpening process. First, we're converting our color image to grayscale, which is necessary for edge detection.
Now we're applying the canny edge detection algorithm to our grayscale image, with lower and upper thresholds of 100 and 200.
We're converting the edge detected image back to a 3-channel image so it's compatible with our display function. We're updating our processing history to include the sharpening operation. This line updates the display with the reverted image. This displays a warning message telling the user no image is loaded to create a histogram. Here we're defining a method to adjust the brightness of our image based on a given value. We're checking if there's an image loaded before proceeding with the sharpening process. We're converting the input value to an integer to use as our brightness adjustment. We're checking if the brightness adjustment is non-zero before applying changes. If the brightness is positive, we'll increase the image brightness. We're calculating the alpha value for our brightness adjustment. We're setting gamma to our shadow value for the brightness adjustment.
Now we're applying the brightness adjustment using OpenCV's add weighted function.
Here we update the display with the reset image. This displays a warning message telling the user no image is loaded to create a histogram. We're defining a method to adjust the contrast of our image based on a given value. We're checking if there's an image loaded before proceeding with the sharpening process.
We're converting the input value to a float to use as our contrast adjustment factor.
We're applying the contrast adjustment using OpenCV's convertScaleAbs function, where alpha is our contrast factor and beta is set to 0. Here we update the display with the reset image. This displays a warning message telling the user no image is loaded to create a histogram.
Here we're defining a method called update processing history that will keep track of the changes made to the image.
This line adds a copy of the current processed image to the processing history list, allowing us to undo changes later.
Now we're defining the undo method, which will revert the image to its previous state.
This condition checks if there's more than one item in the processing history, meaning we have previous states to revert to. If we can undo, this line removes the most recent image from the processing history. Here we set the current processed image to the last item in the processing history, which is now the previous state. Here we update the display with the reset image. This displays a warning message telling the user there are no more actions to undo. Here, we're defining the reset method, which will restore the image to its original state. This checks if we have an original image to reset to. If we have an original image, this line sets the processed image back to a copy of the original. This resets the processing history to only contain the original image. Here we update the display with the reset image. This displays a warning message telling the user there's no image to reset. Now we're defining the showHistogram method, which will display a histogram of the image. We're checking if there's an image loaded before proceeding with the sharpening process. If we have an image, this line converts it to grayscale for the histogram. This creates a histogram of the grayscale image using matplotlib. Here we set the title of the histogram plot. This displays the histogram in a new window. This displays a warning message telling the user no image is loaded to create a histogram.
This condition checks if the script is being run directly, not imported.
If the script is run directly, this creates the main window for our application. This creates an instance of our image processing application. Finally, this starts the main event loop of the application, allowing it to respond to user interactions. In this project, we will develop an advanced image glitch art generator using Python, where users can transform their photos into creative glitch art right from a simple graphical user interface. Leveraging libraries such as OpenCV, tkinter, and PIL, the project allows users to load images, apply various glitch effects, and adjust image properties such as brightness, contrast, saturation, and more. The interface provides a canvas to display images as they are manipulated, alongside a range of buttons and sliders for applying effects like pixelation, noise addition, color inversion, and retro filtering. Additionally, the project incorporates functionality for undoing and redoing changes, enhancing the user experience by allowing flexibility and experimentation. We're defining a new Python class called glitchArtGenerator that will encapsulate all the functions and variables related to our image glitch art program. Here we're creating the initialization method of our class, where we set up our application's main window and its components. This line initializes our main application window using tkinter's tk class, the starting point for our GUI application. We're setting the title of our application window to Advanced Image Glitch Art Generator. This specifies the size of the application window to 1000 pixels wide and 800 pixels tall. A canvas widget is being created, which serves as an area where we can draw or place images, set to $800 600 pixels. We're adding the canvas to the application window and adding a 10-pixel padding around it vertically using the pack method. Here, we're creating a frame to serve as a container for our buttons within the main application window. We then add this button frame to the window with a 10-pixel vertical padding.
This line initializes another frame, which will hold our effect options.
We pack the effect frame into the window, similar to the button frame, with a vertical padding for separation. A call is made to the createButtons method, which will populate our button frame with buttons. This calls the Create Effect Options method for setting up effect options related to image manipulation. We're initializing a variable to hold the original image file, starting off as none since no image is loaded yet. This variable will keep track of the current working version of the image as we apply effects. Initially set to none. Here we define an undo stack as an empty list, which will help us handle undo actions. Similarly, a redo stack is initialized as an empty list to track redo operations. This sets up a protocol to handle window closing events gracefully by calling the onClosing method. Finally, we start the main event loop of the tkinter application, which waits for user actions to process. In this method, we're setting up various buttons with specific functions for user interaction within the app. We start by defining a list of tuples that pairs button labels with their corresponding command functions. This tuple indicates that the Load Image button will trigger the Load Image method when clicked. The Apply Glitch button is associated with the Glitch Image method to produce a glitch effect. This specifies that clicking Save Image will call the Save Image method to store the current image. We map the Undo button to a method that will revert the most recent change using the Undo method. Likewise, the Redo button will reinstate changes using the Redo method we've set up. The Reset button will bring back the original state of the image by invoking the Reset Image method. This bracket closes the list of effect tuples we've just defined. We iterate over each button text and command function pair to create buttons in our UI. A button widget is created for each pair, placed within the button frame with specified text and function. Each button is then packed into the frame positioned to the left, with a slight horizontal padding for spacing. This method is dedicated to setting up option controls for image effect adjustments, augmenting user interactions. We're starting an effects list that specifies available adjustments users can make to images.
For instance, this option relates brightness to the Adjust Brightness method to change the image's brightness.
Here we're creating a list of tuples where each tuple consists of a string representing the name of the effect and the corresponding method to apply that effect, starting with contrast. Next, we add another effect called saturation to our list, again pairing its name with the associated method self, adjust saturation. Adding to our effects list, we include blur and link it to the method self. Apply blur to modify the image's blurriness. We continue by adding sharpen to the effects list with the method self. Apply sharpen to enhance image details. Next up in our effects list is pixelate. Tied to self, apply pixelate for the pixelation transformation.
We also want the option to invert colors, so we add invert colors to the list, with self.invertColors as the corresponding method.
The add noise effect, linked to self-add-noise, is added next, allowing us to introduce random variations to the image. We include vignette as an effect which applies a darkening effect around the edges using self. Apply vignette. Finally, for a vintage aesthetic, we add retro filter to the list, paired with self-apply retro filter. This bracket closes the list of effect tuples we've just defined. We now loop through each effect tuple in our effects list, unpacking it into text and command variables for further use. For each effect, we create a button in the effect frame with the text as its label and the command as its function to apply the effect. We position each button to the left side of the frame with a small padding of 3 pixels between them.
Let's define a method loadImage that will handle opening and loading an image file into our application.
We use a file dialog to let users select an image file, filtering for common image formats. We check if the user selected a file, only continue if they did. Assuming a file was selected, we read the image into self-original image using OpenCV's imread function to store the original image data. We make a copy of the original image and store it in self.currentImage for manipulation. We then call the showImage method to display the current image in the UI. To maintain image editing history, we clear the undo stack whenever a new image is loaded. Similarly, we clear the redo stack to ensure a clean slate for the new image.
Here's the showImage method, which will convert and display the provided image in our application.
We convert the OpenCV image from BGR to RGB format, which is more compatible with the libraries we're using for display.
Next, we convert our NumPy array into a PIL image object for easier manipulation and display.
We resize the image to fit our application window using the Lanczos filter for high-quality downsampling. To display it in a tkinter canvas, we convert the PIL image to a photo image. We place the image onto the canvas, anchoring it to the top left corner. We store a reference to the image in the canvas to prevent it from being garbage collected. Here's a custom method called apply glitch that alters an image with a glitch effect based on the given intensity. We start by making a copy of the input image to avoid modifying the original directly. We extract the dimensions of the image, necessary for determining how to apply the glitch. We perform the glitch operation a number of times equal to the specified intensity. We generate a random offset for RGB channels, ranging between 10 and 10 to create the glitch effect. We randomly choose the height of a slice to apply the glitch, ensuring it isn't too small or large relative to the image. We determine a random starting row for the slice to apply the glitch effect. We shift the pixels in the slice horizontally by our random offset, altering only the selected slice. Finally, we return the modified image, which now contains the glitch effect. We define the glitch image method to facilitate user interaction when applying the glitch effect. Before proceeding, we check if an image is currently loaded. If not, we can't apply the glitch. If no image is loaded, we show an error message using a message box and halt further processing. Early exit from the function if the current image is not loaded. We prompt the user to enter the desired intensity for the glitch effect, ensuring it's between 1 and 20. We check that the user provided an intensity value before applying the glitch effect. Here we are adding the current state of our image to the undo stack, so we can go back to it if needed. In this line, we apply a glitch effect to our current image using a specified intensity level.
Now we update the current image to be the one with the glitch effect applied. This function call is responsible for displaying the modified current image on the screen.
We're checking if there's an image currently loaded as a precaution before saving.
If there is no image loaded, we show an error message to inform the user.
We exit the function early since there is no image to save currently. We're checking if the user specified a path for saving. If not, we won't proceed. This line saves our current image to the specified file path using OpenCV. After successfully saving the image, we display a success message with the image's save location. We're storing a copy of our current image onto the undo stack for future undo actions. We clear any redo actions since a new command breaks the redo chain. We're checking if there is anything to undo by looking at the length of the undo stack. If an undo is possible, we first copy our current image onto the redo stack. We then pop the last saved image from the undo stack and set it as the current image. Finally, we display this newly restored image on the screen. Here we check if there is any action available to redo which is stored in the redo stack. If there is, we first store the current image onto the undo stack for safety. We retrieve the latest image from the redo stack and set it as our current image. Let's display the restored image from the redo stack onto the screen. Before resetting, we need to ensure that we have an original image loaded for resetting. We save our current image to the undo stack before resetting to the original. We copy the original image back to the current image, effectively resetting it. After resetting, we show the original image on the screen. We're checking if there's an image loaded to adjust brightness. Otherwise, we show an error. An error message pops up if there's no image to adjust. We return early from the function because there's no point adjusting the brightness of a non-existent image. We check if a valid brightness factor was provided by the user. We save our current image in the undo stack because we're about to alter it. We convert the current image from OpenCV's BGR format to PIL's RGB format for processing. Using PIL's enhancement tools, we create a brightness enhancer instance for our image. We apply the chosen brightness factor to enhance our image. Convert the enhanced image back to OpenCV format, updating our current image. Lastly, we display the brightness adjusted image on the screen. We're checking if the current image is not loaded to handle any operations on an image. If no image is loaded, show an error message box to the user with the message, "No image loaded." Stop the function from executing further since there's no image to work with. Ask the user to input a contrast factor value between 0.1 and 2.0 using a dialog box. Check if the user provided a contrast factor to proceed with the contrast adjustment. Save the current state of the image to the undo stack to allow reverting changes if needed. Convert the current image from a NumPy array in BGR format to a PIL image in RGB format for processing. Create a contrast enhancer object for the PIL image to adjust its contrast. Apply the contrast adjustment to the image using the factor provided by the user. Convert the enhanced image back to a NumPy array in BGR format to update the current image. Display the updated current image after adjusting the contrast. Define a function to allow the user to adjust the saturation of the current image. We're checking again, this time to ensure an image is loaded for saturation adjustment. If no image is loaded, display an error to prevent any adjustments without an image. Exit the saturation adjustment function if there's no image available. Prompt the user to input a saturation factor between 0.0 and 2.0 with a dialog box. Proceed with saturation adjustment if a valid factor is given. Add the current image state to the undo stack before making changes. Convert the BGR image to an RGB PIL image for manipulation. Create a color enhancer object to modify the image's saturation. Enhance the image saturation based on the factor provided. Convert the modified PIL image back to a BGR NumPy array. Show the updated image with the adjusted saturation to the user. Define a function to apply a blur effect to the current image using user input. Check if an image is loaded before attempting to blur it. Display an error message if no image is available to blur. Exit the blur function if no image is loaded. Ask the user for a blur radius between 1 and 10 via a dialog box. Continue with blurring if a valid blur radius is specified. Store the current image in the undo stack before applying the blur. Transform the BGR image into an RGB PIL image. Apply a Gaussian blur to the image with the specified radius. Convert the blurred image back to BGR format. Display the blurred image for the user to see. Define a method to sharpen the current image to enhance clarity. Ensure an image is loaded before applying the sharpen filter. Notify the user of an error if trying to sharpen without an image. Stop the sharpen function execution if there's no image. Add the current image setup to the undo queue to revert changes if needed. Convert the image to a PIL format for sharpening. Sharpen the image using the PIL image filter Sharpen. Reconvert the sharper image back to OpenCV's BGR format. Reveal the sharpened image so the user can see the changes. This function starts the pixelation process on the current image. First, check if there's an image to work with before pixelating. Alert the user with an error dialog if there's no image loaded yet. This line exits the current function and will not execute any code below if it is reached. This line prompts the user to enter a pixel size between 2 and 50 using a simple dialog box and stores the result in pixel size. This condition checks if the user provided a valid pixel size before proceeding with the next operations. Here we save the current state of the image to an undo stack, allowing us to revert changes later if needed. In this line, we extract the height and width dimensions of the current image for use in resizing operations. We resize the current image to a smaller version by dividing its width and height by the pixel size, using linear interpolation for resizing. This command resizes the smaller version back to the original dimensions using nearest neighbor interpolation, creating a pixelated effect. Finally, we display the updated image with the pixelated effect applied. This line marks the start of a new function that will invert the colors of the current image. We check if there is no image currently loaded, which would prevent further operations. If no image is loaded, an error message is displayed to inform the user. We exit the function early since there's no image to operate on. Like before, we save the current image state to the undo stack before making any changes. Here we invert the colors of the current image by applying a bitwise NOT operation. We then display the image that now has inverted colors. This line begins a new function that will add random noise to the current image. Again, we check if an image is loaded before proceeding with adding noise. An error message is shown if there is no image to apply the noise to. We return from the function early if there's no image. The user is prompted to enter a noise amount between 1 and 50, which determines how much noise will be added. This checks if the user provided a valid noise amount, ensuring we only proceed with valid input. We save the current state of the image to the undo stack before modifying it. A noise array is generated with random integers between 0 and the specified amount, matching the shape of the image. The generated noise is added to the current image, altering its pixel values and introducing noise. Finally, the noised image is displayed for the user to see. This line defines a new function that applies a vignette effect to the current image. We confirm that an image is loaded before attempting to apply the vignette effect. If there's no image, we show an error message advising the user. We exit early from the function if there is no image available. The user is asked to specify an intensity for the vignette effect, with allowed values ranging from 0.0 to 1.0. We proceed only if a valid intensity is provided by the user. The image's state is saved to the undo stack before applying the vignette effect. Here we get the number of rows and columns of the image, which represent its dimensions. We create a Gaussian kernel for the columns, which will help in creating the vignette mask. Similarly, a Gaussian kernel is created for the rows. The kernel for the vignette effect is formed by multiplying the row and column kernels. A mask is created by normalizing the kernel and scaling it to have max value of 255. The mask is blended with intensity to determine the final vignette effect strength. The image is multiplied by the mask to apply the vignette effect pixel-wise. We ensure all image pixel values remain between 0 and 255 after applying the effect. The modified image with the vignette effect is displayed. This line begins the definition of a new function that will apply a retro filter effect to the current image. We check if an image is currently loaded to ensure we can apply the retro filter. An error message alerts the user if no image is available to filter. The function exits early if there's no image loaded. The image's state is saved to the undo stack before applying the vignette effect. We're converting the current image from OpenCV's BGR format to the RGB format using CV2, and then creating a PIL image instance from the NumPy array, which is necessary for applying certain image processing techniques in PL. Here we split the RGB image into its individual red, green, and blue channels so that we can manipulate each color separately. We're adjusting the red channel by multiplying each pixel value by 1.3, which effectively boosts the intensity of reds in the image. In this line, we decrease the intensity of the blue channel by multiplying each pixel value by 0.8, which will make blues in the image less prominent. Now we merge the individually adjusted red, green, and blue channels back into a single RGB image using PIL's merge function. We create an image enhance object to increase the contrast of our image, which will make it look more vivid. Using the enhancer, we boost the image contrast by a factor of 1.2, slightly enhancing the differences between lighter and darker areas. After adjusting the image with PL, we convert it back to OpenCV's BGR format because it's the default color space for display and further processing in OpenCV. Finally, using a function called showImage, we display the processed image, updating it to reflect all the changes made. This line of code checks if the user confirms to quit the application by presenting a message box with quit and "Do you want to quit?" prompt. If the user chooses to quit, we call the destroy method on the app object to close the application cleanly. At the script's entry point, an instance of the glitchArtGenerator class is created, which triggers its initialization and any related operations.